Imagine standing at the edge of a dark beach as the tide pulls back grain by grain. The water is not rushing, it is quietly leaving, and if you hesitate, the shells and stones you came to find will be gone before you bend to pick them up. That is how the sky feels tonight. Our tide is time, and the sea is a small traveller named 3I Atlas, an interstellar comet on a one-way pass by our sun. It does not threaten Earth. There is no danger to prepare for, but there is a narrow window to learn, and the sun's growing glare is already slipping its bright hand over the scene. In the next hours and weeks, the comet will glow, shed dust, paint a faint green haze, and then fade. Science is why we hurry. A visitor from another star carries clues about how worlds begin, and those clues dissolve in sunlight. This film will walk you through what we know, what we are racing to measure before perihelion, and why the most exciting moments are often the hardest to see. You will leave with a clear map of the stakes, the tools, and the plan. If you care about careful, hype-free space storytelling, tap like, subscribe, and turn on notifications so you can follow each chapter as new observations arrive. We start with a simple truth that sets the tone for everything that follows. Our guest will not circle back. It has one arc through our neighborhood, and so do we through its evidence. In the next part, we meet the traveler and learn why one chance changes how you look at a night sky. Picture a single express train that never slows for the platform. You can hear it coming, you can feel the rails hum, but no schedule brings it back tomorrow. That is 3I Atlas. It is not a regular commuter on a loop around our sun. It is a traveler from deep space, gliding through our neighborhood once, then vanishing into the dark again. The urgency you hear in astronomers' voices does not come from fear. It comes from the knowledge that the evidence we want most will be gone when the engine has passed and the tracks fall silent. This comet is interstellar. That simple fact changes the mood of the whole story. Most comets seen from American backyards belong to the sun in the sense that their paths are closed, stretched ovals that bring them back after decades or millennia. They are residents, even if reclusive ones. 3I Atlas is different. Its path is open, the sun bends it, but cannot keep it. When people ask whether it will return in a few years, the honest answer is no. It will not loop around for a second chance, and we cannot ask the sky to repeat itself. There is relief in saying what this is not. It is not an object on a collision course with Earth. It will never graze our air, never redraw a coastline, never flash across the daytime sky with danger attached. That clarity matters for viewers and for schools, considering whether to use a segment like this in a classroom. Safety is the baseline, and once that is set, we get to talk about what makes this such a rare opportunity. The rarity is the point. Once the window closes, whatever we fail to measure becomes a permanent blank space in the record. The word that unlocks this chapter is unbound. An unbound path means gravity does not win custody. The sun pulls, the comet accelerates, and then it keeps going. There is a small vocabulary around that idea, but you do not need the vocabulary to feel the stakes. What you need is the image of a guest at an open house who reads the note on the door and knows there is no return ticket in the envelope. Scientists love return tickets. Return tickets mean you can check your work in a few years. With 3I Atlas, there is only the visit on the table right now. Here is a simple fact that can be hard to swallow in a culture that prizes second tries. Nature does not promise do-overs. That is not a rule made by astronomers. It is geometry written into the way gravity and motion share the stage. The comet's speed is part of that geometry. Fast means hard to keep. Fast also means moments of activity can burst and fade while you sleep. People sometimes imagine that big space events must be slow. The paradox is that the big ones can be over before you can reschedule a telescope. That is why observers in Arizona, Hawaii, Chile, and space are synchronizing like a relay team that cannot drop the baton. Quick explainer, in everyday terms, on what it means to have an unbound hyperbolic path. Think of throwing a ball up a hill. If you throw it gently, the ball rolls back, and you get it again. If you throw it harder, it climbs higher, slows, and still returns. But if you throw it with enough speed, it crests the hill and never comes back to your feet. A hyperbolic orbit is the space version of that last throw. The sun is the hill. The comet has enough speed to crest and keep going. Bound orbits are like tethered dogs circling a yard. Unbound paths are like a bird crossing a valley, winging onward once it passes the ridge. The difference is not poetry. It decides whether we can plan a second attempt or not. There is another way to feel the one-chance nature of this story, and it has to do with the clock on the wall. Even in the United States, where we are used to on-demand shows and next-day shipping, the sky does not bend to our convenience. If a good night for spectroscopy falls on a Tuesday, that Tuesday counts. If the following Thursday is cloudy from Seattle to San Diego, that lost time does not replace itself. The comet is not waiting for a clear forecast. When astronomers sound brisk, they are not rude. They are translating the calendar of the cosmos into the calendar on your phone. I want to share a personal view here, not as a verdict, but as a way to frame the next hours. To me, single chance phenomena are where science and humility meet. They force us to be honest about what we can and cannot do and to choose carefully. I also think they bring out a gracious kind of collaboration. When you cannot own the moment, you share it. The best observing campaigns for objects like this feel less like a contest and more like a barn raising. You might ask how we know the comet is interstellar, if it is just a fuzzy dot and a thin tail. The answer begins with the shape of the path, which points to a speed too high for the sun to capture. It continues with the way the tail forms and the kinds of light we see, which match the behavior of natural ice and dust, warmed for the first time in ages. None of that requires exotic explanations. The beauty here is that ordinary physics, applied to an extraordinary visitor, is more than enough to justify the rush. There is a small temptation, especially online, to attach legends to a traveler who comes from far away. I understand the urge. Distance feels mysterious, and mystery invites stories. But distance by itself is not a story. What makes the visitor worth your time is not where it started. It is the sample it carries. Dust and ice encode the conditions of its birth neighborhood. If we read that code with care, we do not just learn about one object. We widen the circle of what we think is normal for planet building across the galaxy. That is why the one chance matters. It is not a trophy. It is a data set with a passport. Think about a typical American evening this week. Someone is grilling in the backyard. Someone is finishing homework at the kitchen table. Someone is driving past a field of wind turbines. Above all of that, a tiny body is warming, as if a freezer door cracked open for the first time. Molecules that sat quietly for ages are waking up and drifting into sunlight. Cameras will catch some of them by their color and glow. Some will slip by, too faint, too fast, or too close to the sun's glare to cleanly measure. That is the risk we live with. You may wonder why we cannot simply watch it later, after it swings by and the glare calms down. The easy answer is that the best chemistry happens when the sunlight is strongest, and that overlaps with the period when the comet is closest to the sun in our sky. The richer the activity, the harder it is to see. Later, when the geometry improves for our eyes, the action is already cooling. We will still learn things then, but the most delicate clues about its birthplace live in the hot phase. That overlap of peak activity and poor viewing is the heart of this one-chance problem. I also want to be transparent about another piece. We speak with care because early signals can change with better data. That is not a flaw. It is the way science protects itself from wishful thinking. If we say that some ratios of gases look unusual, we also say that those numbers need confirmation from different instruments. I believe that caution is a kind of respect for the viewer. You deserve result that will still be true when the season changes and the comet is a memory. Confidence and patience are not opposites. They are partners in stories like this. The idea of a single encounter can feel heavy. it can also feel precious. Consider how we treat one-night performances in a small theatre. The seats are filled. The actors are nervous. The town shows up because this is it. That sense of community is what you will see among observatories right now. The desert hills in the southwest, the high Chilean plateaus, and the orbiting platforms above our heads are all tuned to the same page. Some collect colors we cannot see. Some measure changes in brightness over hours. Some watch for sudden bursts that come like a cough from the nucleus. No single sight can do it all. Together, they weave a net that is strong enough to catch meaning, but light enough to let rumor fall through. There is a practical lesson here for anyone who cares about learning, not just about comets. When you have one class session with a great guest speaker, you plan. You define a few key questions. You decide which activities you can do in the room and which you will assign for later. That is exactly how this observing campaign works. We decide which measurements must happen now, which can wait, and which are nice to have if the sky grants a little grace. There is no shame in triage. There is wisdom in it. Because this is a show for a general American audience, let's keep the heartbeat of the story in plain sight. We are not chasing a crisis. We are chasing understanding. The advance notice is short. The stakes are high for knowledge, not safety. The timelines are set by sunlight and angles. Our tools are telescopes and teamwork, and the outcome we want is a cleaner picture of how other neighborhoods in our galaxy build their first bricks of ice and rock. This is also a place to set expectations. Not every claim you see online will hold up. If someone tells you the comet is doing the impossible, ask what instrument saw it and whether another one agrees. If someone says the chemistry proves a dramatic theory, ask whether there was enough light collected to separate a small signal from noise. These are not gotcha questions. They are the kind of questions that keep the story healthy and keep you in the driver's seat as a viewer. My own opinion, offered with care, is that this kind of one-chance visitor is where public science earns trust. When we say we do not know yet, we should mean it. When we say we have seen something intriguing, we should be able to show why it is intriguing without asking you to take it on faith. That is the promise I am making in this series. We will celebrate the beautiful parts. We will acknowledge the gaps, and we will resist the urge to turn gaps into fantasies. Let's close this chapter by returning to the image that started it. The express train is almost here. We are not trying to jump aboard. We are trying to read the writing on its side as it passes, and to record enough detail that, when we look back later, we can tell which railroad it came from and how it was built. That is the work. It is modest in its posture and grand in its payoff if we do it well. In the next part, we will show how the messenger was spotted in the first place and why catching it early changes everything about what we can learn. Think of a small town that hires a night watch to circle the blocks while everyone sleeps. The watchman does not stare at one porch all night. He walks a loop with a steady pace, checks the same corners again and again, and if a car he has never seen rolls down a side street with its lights dimmed, he notices because it was not there on the last pass. That is how modern sky surveys work. They are the night watch of the cosmos, repeating careful loops, catching what has changed since the last look. On the night our story begins, arrays of wide-field cameras were doing what they do every clear evening. They were tiling the sky into neat rectangles, exposing for just long enough to collect a simple truth about each patch, then moving to the next. A few minutes later, they came back to the first patch and took another image. Computers compared the two, pixel by pixel, almost like those spot the difference puzzles you might play with a child at a kitchen table. Most differences are nothing. Air wiggles. A cosmic ray hits a detector. A satellite streaks by. But sometimes a small, soft point of light has shifted by a hair's width. That is the signature of a traveler. Early notices go out quietly at first. The software names the suspect with a temporary code and calculates a rough path. The number is not poetry. It is bookkeeping, a way to attach new measurements to the same sky dot during the next passes. Within hours, other telescopes are invited to look. Sometimes that means a research instrument on a mountain. Sometimes it means a dedicated amateur in a backyard outside Denver, or in a desert neighborhood near Tucson. The fastest way to learn whether an object is serious is to watch it keep moving night after night. What makes this detection special is not that a new comet was found. New comets are spotted every year. What matters is the lead time. Spotting a visitor weeks before its closest brush with sunlight gives us a longer runway. A longer runway means more time to fit a path. It means we can ask for telescope time instead of begging for it. It means we can design observations that fit together instead of piling on whatever is available. The first hours after a candidate appears are a test of patience. The initial path is fuzzy because it rests on very little information. To know where a commuter is headed, it helps to see where it was all day, not just in one security clip. Astronomers collect a handful of positions across the night and return the next night to extend the line. Every additional dot tightens the curve that best fits the motion. If the curve wants to be open rather than closed, if it looks more like a path that never returns than a loop that will come back, the mood shifts in every control room that cares about comets. This is where the unbound story from the last chapter takes on muscle. There is a simple logic at work. If gravity from the sun cannot turn the path into a long oval, the object must have arrived from beyond the family of orbits that the sun usually shepherds. No one needs arcane equations to feel what that means. You do not need to see the whole road to tell that a car is not circling a block. A few minutes of motion, measured with care, is enough to show that it is leaving town for good. Names change as the confidence rises. The temporary code that helped gather the first nights of data gives way to a formal designation. That designation reflects what we think the object is and where it belongs in the record. The shift from a comet code to the simpler numeric label that says interstellar is a quiet, thrilling formality. It is the moment when the town's night watch radios the station, and the station replies, "We see it too. This one is not ours." Let's pause for a clean, everyday explainer of how a survey finds a moving object. Picture a smartphone set to take a photo of your front yard every 2 minutes. Now imagine laying those photos on top of each other and flicking between them with your thumb. Leaves shake, porch lights glow, a moth flashes and disappears. If your neighbor's cat walks across the lawn between frames, it shows up as a small, consistent shift at the same place, frame after frame. Software does this in the sky. It subtracts a new image from a reference image, flags the leftover dots, and asks whether any of those dots move with the right speed and direction to be a solar system object. The workflow then rejects false alarms and keeps what repeats. From that, positions are calculated on the celestial grid, and those positions feed a fit of the path, the way a baseball coach can predict where a ball will land after watching it for a second or two. Back to the human side. Because this is America, and because this work happens in many time zones, the first night often involves a strange relay. A telescope in Hawaii takes the opening frames. Another in California adds points after midnight. A robot in Arizona picks up the object near dawn. Before lunch on the East Coast, the first orbit fit might be ready. While you drive to a morning meeting, someone clicks send on an alert. While you pick up a child from practice, someone updates the motion plot. It is ordinary life below an extraordinary sky, and the rhythm matters because that is how a community keeps pace with an object that does not slow down for anyone. The early fit is usually checked against older images. This is called pre-covery, and it is as intuitive as checking a home security log to see if a car you noticed today drove by last week. If the object happened to be in a patch of sky that was imaged a few nights earlier, even faintly, those old frames can add precious length to the arc we draw. Longer arcs shrink the uncertainty in the path. Shrinking that uncertainty tells everyone which part of the sky to aim at tomorrow. The difference between a path that is a mile wide and one that is the width of a driveway is the difference between guessing and planning. One of the least glamorous and most important jobs in this process is rejecting the fakes. Satellites streak, planes blink, detectors cough, meteors flash. A good survey pipeline knows the signature of each distraction and drops them from the list. Here is where human judgment still adds value. A researcher looks at a set of thumbnails and says no to dots that move wrong, flare wrong, or trail like a passing aircraft. That curation keeps the catalogue clean and keeps telescope time from being wasted. Discovery is never a solo act. The announcement that a candidate may be interstellar draws partners. A spectrograph in Chile measures color and hints at chemistry. A mid-infrared camera in orbit looks for warm dust. A photometer tries to see if the brightness wiggles in a way that would give away a rotation period. None of these instruments can do the whole job. Each is a lens on a different part of the story. Early detection gives those lenses time to coordinate. There is a practical American example that mirrors this teamwork. If a wildfire starts in a national forest, the first helicopter that spots smoke does not put it out. It calls in other assets that carry water, map the wind, and clear evacuation paths. Each asset has limitations. Each is essential. The sooner the smoke is logged, the more realistic the plan becomes. In astronomy, the smoke is the moving dot. The water is the time on a telescope that can separate light into its components. The evacuation path is the plan to observe before the sun's glare closes the road. The word messenger in this part's title is not romantic padding. It points to what a comet like this can carry. In the first days after discovery, the spectrum is often blank or faint, but even a faint, sloped smudge can say something about dust size. Even a soft green smear, if it appears, can indicate carbon-rich fragments waking up. When those hints align with the motion fit that says unbound, the field feels the gravity of the moment. It is as if the night watchman has not only seen a new car, but also noticed the logo on its hubcaps from a make no one in town sells. Here is my personal view, offered plainly. Early discovery is the oxygen of this kind of science. It brings out the best in our habits. People share data more easily because no one can cover the sky alone. Claims arrive with measured language because there is time to check, not just to shout. I believe the public senses the difference. When a story unfolds at a human pace instead of a panic pace, trust grows alongside the plot. The educational piece I want to add here is about confidence and revision. In the first week, orbit solutions improve because more data means a firmer grip on the path. If you see a number change on a chart, it does not mean someone made a mistake. It means the math is responding to better input. Think of getting a weather forecast for a road trip. On Monday, what the model says, rain in the afternoon. On Wednesday, after new satellite images arrive, it says light showers in the morning instead. You do not accuse the meteorologist of lying. You understand that fresh information refined the call. Astronomy is the same. We do not etch first guesses in stone. We let them evolve as the sky gives us more to work with. There is a subtle benefit to early spotting that is easy to miss. It allows us to build a baseline. A baseline is a portrait of the comet when it is still quiet. Later, when the activity rises, we can see what has changed. Without that early calm frame, it is hard to judge whether a later surge is unusual or simply the normal ramp-up as sunlight climbs. Baselines make the difference between drama and context. When you look back at a child's height chart, you learn the shape of growth. We crave the same shape in a comet's light. Time allocation for large telescopes is another reason the first notice matters. The biggest instruments in the world run on schedules built months ahead, with small windows reserved for targets of opportunity. An interstellar comet earns a seat at that table if the case is made quickly and clearly. The case is stronger when the path is known, the brightness trend is measured, and the chemistry hints are specific. In that sense, the discovery team is not just finding a thing, they are writing a grant in the sky, asking for a chance to use tools that millions of people paid to build. Communication with the public begins here as well. A short, calm post that explains what has been seen without overpromising, is worth more than a flashy claim that crumbles in a week. Teachers in Ohio, park staff in Utah, and families in Georgia will decide whether to follow this story based on whether we treat their attention like the scarce, generous resource it is. I like to imagine a science teacher skimming a summary before first period and thinking, we can spend 5 minutes on this today and then check back next week. That is how attention becomes learning. Another practical piece in the first days concerns brightness. A comet's brightness is a dance between how much dust and gas it releases and the angles of the sun, earth, and comet. The early measurements are often noisy. Streetlights, thin clouds, and moonlight can blur the numbers a little, but even rough magnitudes tell us whether a comet is lively or quiet for its distance. If the curve climbs faster than expected, instruments that can separate light into colors are moved up the list. If it lags, planners adjust and ask different questions. This is not indecision, it is good triage. If you grew up with baseball, you know the skill of reading a ball off the bat. An outfielder takes a first step in the right direction and then corrects as the arc becomes clear. It is a perfect analogy for orbit fitting. The first measurement is the crack of the bat. The next dozen are the arc. No one waits until the ball is halfway down to begin to move. That is how astronomers behave in the first week. We move on, good starts, and refine as the arc sharpens. Interstellar becomes the working assumption when 3 things line up. The speed is too high for capture. The path refuses to close into a loop when more days are added, and the brightness behavior matches what we expect from a natural object warming for the first time. Each piece by itself is suggestive. Together, they are persuasive. That is the moment when you turn a corner from maybe to probably and begin to plan for the deeper questions of chemistry and structure. There is also a social moment hidden inside discovery. Credit matters because names on papers and notices fuel careers. But on nights like these, sharing matters more. If a backyard observer in Texas contributes 5 perfect measurements that sharpen the path, the professionals will remember. If a graduate student writes a script that rejects false alarms better than last year's code, that skill will travel with her. Early discovery is a forge. It shapes how a field treats the next big thing. Throughout these first days, the story remains grounded by 2 simple sentences. The visitor will not hit Earth. The visitor will not return. Once those are in your pocket, everything else can be framed as an invitation to learn. You do not need a bunker. You need curiosity, and if you can spare it, a little patience for the way real-time science evolves. Put yourself for a moment in the chair of a scheduler at a major observatory. A cue screen shows a long list of approved programs. A note arrives about a newly designated interstellar comet with rising activity. The question is not whether the comet is interesting, it is how to weave it into a night without breaking every promise already made. Early discovery gives you options. You can trade half an hour here for an hour there. You can call a colleague and coordinate so that 2 instruments work in tandem instead of duplicating effort. Options are the currency of good observing, and they are minted in the first days. I want to close this chapter's argument with one more honest opinion. The best thing early discovery gives us is the chance to be generous with our own uncertainty. When you have time, you can admit what you do not know without losing the plot. You can explain that a green glow might grow or might not, that a rise in dust might belong to a jet turning toward the sun or might be a simple spike that will fade by Friday. Audiences respond to that tone. They do not need swagger. They need a guide who knows when to step back and watch before speaking. So the night watch did its job. The path was flagged. The call went out. The circle of instruments widened. The public was invited in, not to panic, but to watch with intent. We have a guest on one pass through town, and we have a chance to greet it well, with cameras ready and minds calm. In the next part, we peer closer at what the traveller does as sunlight strengthens. We will watch how a cold nucleus wakes, how a haze forms, and why a faint green can spell out a chemistry lesson written across the dark. Picture a chest freezer in a quiet garage at dawn. Someone cracks the lid, and a soft breath of cold drifts out. Frost crystals hiss as warm air slides in, and for a few seconds, you can almost hear the ice adjusting to a world that is suddenly brighter. That is the mood around 3i Atlas right now. After ages in deep space, it is meeting sunlight it has not felt in a very long time. And the response is simple and beautiful. Ice turns to gas. Gas lifts dust. A halo forms. From Earth, that halo looks like a faint candle flame around a pinprick core. Up close, it is the start of a weather system made by a snowball that is waking up. A comet begins as a dark nucleus, a compact mix of ices and rock held together by gravity and cold. When sunlight strengthens, the outermost grains warm first. Molecules trapped between dust particles begin to loosen their grip. They slip free, drift upward, and carry tiny specks of powder with them. Layer by layer, a thin atmosphere gathers around the nucleus. Astronomers call that atmosphere the coma. It is not as thick as air at sea level. It is delicate, almost a whisper, but it is enough to scatter sunlight and give the comet a soft face. In that soft face, chemistry writes its own script. Some gases are common, like water vapor and carbon dioxide, because the ices that release them are easy to make in cold places. Others are present in smaller amounts and act like spices in a recipe. As these gases absorb sunlight, their molecules rearrange and glow. The glow is not like a neon sign that stays one color. It changes with distance from the sun, with the heat of the day, and with the supply of fresh material from the surface. That is why images taken a week apart can look like the same painting touched up by a different hand. The tale is born, where the coma flows outward and meets two forces that push it on. One is sunlight itself. Light carries momentum. On grains as small as smoke, that push is enough to nudge them away from the sun, and a dust tail begins to stream out like a slow banner. The other push comes from charged particles in the flow of solar wind. Those particles sweep gas into thin, straight strands that sometimes split or kink under changing conditions. That is the ion tail. Most backyard images blend both tails into one pale brushstroke. With practice and the right filters, you can tell them apart. The dust tail often looks warmer and more curved. The ion tail can look cold and blue, an arrow pointing away from the sun. There is a special kind of green that comet watchers talk about. It is the green of C2, two carbon atoms linked and briefly excited by sunlight. On camera sensors, that green sits in a band of visible light that the human eye is good at. When C2 is present, the inner coma can take on a sea glass hue. It does not mean the nucleus is emerald. It means the chemistry in the shell is lively, breaking down more complex carbon-rich materials and reassembling them in a way that glows for a short time. The glow is transient. Sunlight that turns it on also tears it apart. That is why the green often hugs the region close to the nucleus and fades farther out. The comet is making the color and losing it at the same time, a dynamic balance that lasts as long as the ice feeds it. From a distance, awakening looks smooth, but the surface story is more uneven. Not all patches of the nucleus receive sunlight equally. If the comet spins, some regions face the sun and then turn away. Pockets of more volatile ice can erupt faster than their neighbors. Jets form where the crust cracks or where soft dust gives way, and those narrow plumes add structure to the coma. In long exposures, the jets can leave faint fans or spirals that record the spin of the body, the way a sprinkler records its own rhythm on a summer lawn. Catching those patterns is one of the real joys of comet work. They turn a point of light into a rotating world with personality. There is a practical reason to pay attention to this early weather. When a comet first wakes, the gas flow is modest and the coma is thin. That is good for some measurements, because thin means we can still see hints of the nucleus through the haze. As activity increases, the coma thickens and the nucleus disappears more completely. Through all of this, we try to read signals that are faint and layered. One line in the spectrum tells us water is present. Another hints at carbon dioxide that may be unusually abundant for a comet at this distance. Each line is a clue, and each is easier to measure before the sky grows too bright near the sun. Educational moment, kept plain and short. Sublimation is the key word here. It means an ice that turns straight into a gas without passing through a liquid stage. Dry ice is a familiar example from a theatre stage or a Halloween bowl. In space, ordinary water ice can also sublimate because the pressure is so low and the sunlight is strong enough to break the bonds holding molecules in place. When those molecules leave, they carry energy with them. That cools the surface slightly, but it also loosens dust grains and opens tiny pathways in the crust. The result is a slow boil that begins well before you see anything dramatic. And that slow boil is enough to build a coma that grows from the size of a city to the size of a planet's orbit if the comet is active and time allows. From my own point of view, the beauty of this process is its honesty. There is no trick here, no hidden engine. It is ice and sunlight doing what ice and sunlight do. I also feel the limits of the view from Earth. There are moments when you want to lean in and see the texture of a crack or watch a jet pulse in real time. We cannot. We are readers on a hill looking at a valley with binoculars. The discipline is to embrace the distance and let careful methods make up for the miles. One of those methods is to watch how brightness rises with time. A comet that wakes steadily suggests a surface that is more uniform, or at least not dominated by one geyser. A comet that brightens in jumps might be turning a set of active patches toward us, or might have pockets that let go in bursts. Neither case is better or worse. They are different pathways to the same kind of coma, but they teach us different lessons about how the nucleus is built. Does it have a thin crust over a softer layer, or a rough skin with many small vents? Does the spin tilt the same way a top leans, or is it tumoring? These are hard questions to answer from far away, yet the brightness curve and the shape of the coma can whisper back if we listen long enough. Color adds more context. Blue hints at ionized gases. Yellow-brown hints at sunlight scattered by small dust. Green from C2 tells us carbon chemistry is awake. If someone says the color is proof of something unique, a good follow-up is to ask how bright and how close to the nucleus that color sits. Many comets wear a green scarf near the core as they warm. The interesting question is not whether the scarf exists, it is how strong it is for this comet at this distance and how it changes with time. Ratios matter more than snapshots. A single frame is a postcard. A month of frames is a diary. Another helpful test is to watch how the tail bends. Dust is pushed by light curves because the comet itself is moving along its path, while the dust falls behind. The stronger the pressure of sunlight on small grains, the more the tail arcs. If the tail has kinks or straight, narrow features, the solar wind may be writing its own notes into the scene. In big solar storms, those notes can change in hours. For a one-pass visitor like 3i Atlas, the chance to see the tail react during the run-up to perihelion is a gift. It lets us sample the comet's sensitivity to space weather in a way we rarely can on such a tight clock. We also look for the green to come and go the way a neon sign flickers when the power supply dips. In the coma, the source of the green is constant only if fresh carbon-rich material keeps being fed, and the sun's ultraviolet light has the right balance of intensity to excite and destroy the C2 at a steady rate. If either changes, the color changes. That dance, measured night by night, is one of the best ways to tie a picture of chemistry to a picture of behavior. Is the comet shedding dust in a gentle breeze or in gusts? Is the gas flow smooth or chopped into segments by spin? The light does not tell us everything, but it can narrow the menu. We should also say what this awakening is not. It is not a sign of the comet coming apart in a way that would scatter giant fragments across space toward Earth. Most comets shed mass when they are active. That is the point. They lose a surface skin and build their own cloud. Over many passes, a bound comet can wear itself down. For an interstellar visitor on one pass, the story is shorter and simpler. It wakes, it breathes, and it slides away colder than it arrived. a little smaller, a little lighter, a little better known. There is one more human element. From observatories in the southwest, the best nights for watching the coma grow often arrive just as fall sports fill bleachers and hayfields take their last cuts. That means the people doing this work are pacing between family life and control rooms, like everyone else in the country, balancing what matters at home and at work. When we talk about the beauty of a green coma, remember there is a person at a console holding a cup of coffee and deciding whether to take one more exposure or move to a different filter before the comet dips too low. Science is a team sport played under odd hours. For teachers and curious viewers, here is a simple exercise to make the coma and tail more vivid without formulas. Take a flashlight and a tray of flour outside at night. Sprinkle a thin line of flour into a light breeze and shine the light at an angle. You will see a small plume where the grains lift and drift. If you move while you pour, the plume will curve behind you. If the wind shifts, the plume will kink. Replace flour with glitter, and you will catch more brightness near the source and a faster fade with distance. That little kitchen table experiment carries the spirit of what sunlight and solar wind do to a comet's breath. My opinion, again offered as a guide more than a verdict, is that this is the most romantic part of the story. The physics is humble and direct. The pictures are gentle. The stakes are in the details, not in spectacle. We have to tap into a kind of attention that American life does not always reward, the kind that notices a slow change over many nights and finds joy in the curve, not the headline. I think audiences are hungry for that. A quiet light in a dark field is not flashy. It is durable. It teaches patience in a way that leaves room for wonder. The last thing to say in this chapter is about timing. Awakening does not wait for favorable viewing angles. It follows the sun. The closer Three-Eye Atlas draws to perihelion, the more its chemistry will come alive, and the closer it will appear to the sun in our sky. That is the squeeze. It gives us our richest signals in the same weeks when glare and geometry try to wash them away. In the next part, we will look at how the observing network responds to that squeeze, how instruments share the load, and why the next stretch is less a marathon and more a sprint measured in carefully planned nights. If the last chapter felt like dawn on a quiet cul-de-sac, this one feels like a newsroom on election night. Phones ring, maps glow, producers shuffle the rundown, and every screen shows a different angle on the same story. That is what an interstellar comet does to the observing world. It turns routine into a sprint. The goal is simple. Gather the most faithful light before the glare wins and the scene goes off the air. The trick is knowing which questions must be answered now, which can wait a week, and which will never be answerable if we do not move tonight. The sprint begins with a playbook divided by strengths. Wide field surveys keep watch for sudden changes. Big mirrors take deep, steady looks. Space telescopes collect colors that the atmosphere distorts. Small, nimble scopes fill in gaps when clouds or scheduling kinks the chain. None of these players can do the whole job. Together they make a net, and a net only works when every knot holds. That is why planning meetings this week sounds less like lectures and more like briefings. Who has the comet at dusk? Who can hold it through midnight? Who can hand it to the morning shift before the sun claims the sky? On paper, the roles look clean. One team maps shape, another splits light by color, and a third times the tiny wiggles that hint at rotation. Real nights are messier. Twilight bleeds longer than expected. Wind pushes a mount out of tolerance. A camera warms by a degree and changes the way it sees faint green near the core. The people at the controls know this and budget extra frames to catch calibration stars, extra minutes to refocus between filters, extra margin to survive a gust that sends one exposure to the trash. The sprint is physical as well as mental. It feels like running a relay where the track changes slope at random. There is an American rhythm to the handoffs. Sunset in the southwest gives way to prime hours in Hawaii. Chile takes the baton when Arizona bows out. Space keeps watch through the daylight stretch for the continental United States. then passes back to the Pacific as evening returns. In a good week, the comet is never alone for long. In a bad week, a slow front parked over the Rockies cancels a block of time, and the team leans on whatever can observe above the weather. The sprint assumes losses and still aims for a clean story arc. That means redundancy without waste, overlap without duplication, and backup plans that are more than wishful thinking. The biggest choice each night is between depth and coverage. Depth means staring longer to lift faint signals above noise. Coverage means sampling more moments to trace change. Depth is how you catch a shy line that tells you carbon dioxide might be stronger than water. Coverage is how you catch a burst of dust that lasts an hour and never repeats. No budget buys both at once. The art is pairing instruments so one goes deep while another checks the heartbeat. When both report in the morning, the story is richer than either could tell alone. Consider space and ground as a match set rather than a ladder. A space platform sees infrared light that the atmosphere absorbs and can stare through midday. A mountain telescope sees details in the shape of the coma and tail that a distant platform cannot resolve. When the team agrees on a timed sequence, something close to magic happens. The space spectrum says a species brightened at 2 a.m. The ground image taken at the same minute shows a new fan near the sunward edge of the coma. Those two notes together hum a tune you cannot hear from one instrument alone. The sprint's reward is not a trophy. It is two lines of evidence that point to the same cause. Education break, in plain language, on signal to noise, and why everyone keeps saying SNR as if it were a weather report number. Imagine trying to hear a friend whisper across a busy diner. The whisper is the signal. The clatter of plates and hum of conversation is the noise. If the diner gets louder, you need your friend to lean closer or speak longer so you can make out the words. Telescopes solve it the same way. They either collect more light by staring longer or by using a bigger mirror, so the whisper becomes clear against the background hiss of the night, the electronics, and the atmosphere. A high signal-to-noise ratio means the words are sharp and repeatable, not guesses. A low ratio means you might be fooling yourself. That is why observers guard SNR like a pilot guards fuel. Without enough, you can taxi around the runway, but you will not leave the ground. Every sprint needs a play clock. For 3i Atlas, the clock is a mix of calendar dates, solar angles, and brightness trends. The calendar says perihelion is coming fast. The angle says each night the comet sinks closer to the sun in our sky, shaving safe observing time from both ends of darkness. The brightness trend says whether activity is ramping quickly or lazily. A steep ramp favors chemistry now, even if geometry hurts. A slow ramp buys a few extra days for shape and spin. The team revises the clock daily, not because the sky is unreliable, but because new data sharpen what matters most. There is a part of the sprint you rarely hear about in public, and it deserves daylight. Calibration is the quiet twin of discovery. Without it, numbers are just pretty pictures with guesses under the glass. That is why observatories spend precious minutes on images of known stars to correct the night's quirks, on flats to tame dust stuck to the sensor, on dark frames to subtract the camera's own hiss. When a spectrum arrives at 3 a.m., someone checks whether a faint dip is real chemistry or a bruise from a bad pixel. The speed of the sprint does not excuse sloppy habits. It demands better ones. What about cost? In a sprint, minutes on a flagship telescope are expensive, but waste is more expensive. It is better to spend a full hour once with the right setup than to nibble with 3 short sessions that never lift the signal above noise. It is better to stage 2 scopes in tandem for a single rich window than to pepper the week with uncoordinated peaks. This is not stinginess. It is stewardship. People across the United States pay for these instruments. The sprint is how we honor that investment by turning time into trustworthy knowledge. The human factor is everywhere. Night assistants juggle power outages and frost. Graduate students double-check logs. half terrified of missing a line at the edge of detection, and half thrilled to see any line at all. A principal investigator dials in from a kitchen in Virginia, hears that the seeing has improved over Mauna Kea, and approves a longer exposure. A data engineer in New Mexico wakes to a queue of raw files and pushes them through a pipeline, so the first plots are ready before most offices open. The sprint writes its own shift schedule. My personal view, offered in the spirit of transparency, is that sprints like this show science at its most public-spirited. There is urgency without theatre, caution without paralysis, and a genuine pride in making different tools sing in tune. I also believe this is where viewers can feel like participants. When you understand the trade-offs, the choices make sense, and the story becomes something you can discuss at the dinner table without a glossary. What do we actually ask the comet each night? First, we ask what shape the coma and tail have taken, and whether any new jets have carved patterns in the glow. Second, we ask for a taste of chemistry, even a simple ratio that tells us how the balance of gases is shifting with distance and time. Third, we listen for a pulse in the light curve that could betray a rotation period. Fourth, we note the sky's mood around the comet, because a gust of solar wind can rewrite the ion tail, while the dust tail keeps its curved, patient line. These are not random questions. They are the minimum set that lets us tell a coherent, falsifiable story later. Logistics can sound dry until you picture the moving parts. A telescope cannot point near the sun beyond a safe angle, the same way you cannot point your eyes at a welding arc. Every night, that angle trims a little more time from the comet's safe sky. Twilight steals contrast from one side of the night. Moonlight sneaks in from the other. Air masses thicken as the object sinks, adding shimmer and stealing the fine detail you need to trace a jet. The sprint wrestles these constraints onto a calendar. It moves the longest exposures to the darkest half hour, the color sequence to the second best slot, and the quick check frames to the margins, where any data is better than none. Behind the scenes, data sharing has its own tempo. Raw files are large, and the internet can be rural slow on a mountain. Teams compress smartly, send what is needed first, and let the rest trickle in. A Slack channel pings when a spectrum lands. A shared notebook flips from grey to green as a line rises above the noise. Someone posts a plot with axes labelled in plain English, so colleagues with different specialties can read it without translation. These are small courtesies that save hours in a sprint, and hours are the coin we keep spending. Education break 2, on coordination without too much jargon. Think of a city street crew repaving a busy intersection overnight. One team blocks traffic, another scrapes, another pours, and a final crew paints lines before dawn. If any team arrives out of order, the next cannot begin, and the morning rush will hit fresh asphalt with no lanes marked. Astronomy works the same way in a sprint. The path fit must be current before the deep camera can start. The deep camera must finish before the spectrograph can target the right patch. The spectrum must be reduced before the modeler can say whether a faint green grew or shrank. If coordination fails, you might still collect pictures, but they will not line up into a story that survives Monday morning questions. We should talk about mistakes because they happen in sprints. A filter wheel sticks, and you get the wrong color for 5 minutes. A cloud brushes the field during a crucial exposure, and the signal drops. The important part is what happens next. Good logs flag the suspect frames. Good teams repeat the measurement if the sky allows. Good narrators, which is what scientists become when they publish, mark the places where uncertainty swelled and why. The sprint's ethic is not perfection. It is honesty under pressure. Redundancy is not a waste when used wisely. 2 instruments separated by 1,000 miles and a dozen time zones measuring the same line on the same night are insurance against a faulty cable or a calibration flaw. If both agree, confidence rises. If they do not, you have found a seam that needs attention. That seam might be an error. It might be a new phenomenon that only one instrument is sensitive to. Either way, the sprint treats disagreement as a signal, not an embarrassment. A word about priorities in chemistry. With a one-pass object, there is a strong case for chasing the gases that evaporate early and speak to formation conditions. If a ratio of 2 common species looks odd for the comet's distance, that hint deserves time, even if other, easier lines beckon. The sprint protects that time. It also resists the urge to declare a trend after a single good night. So 2 points make a line on a whiteboard, but they do not make a habit in nature. We learn that only by watching the same metrics in a cadence that reveals whether a rise was a one-off or a new baseline. All the while, the public narrative should stay in step with the data. That means updates that say what improved, what surprised, and what could still flip as new light comes in. It means quiet confidence when a line holds for a week, and modesty when last night's rumor fails to survive the morning's reduction. The sprint asks viewers to join us not as cheerleaders, but as witnesses to careful work on a moving target. My opinion, for the record, is that viewers in the United States appreciate this cadence. Clear steps, plain goals, a hint of drama borrowed from the sky, not injected by the script. When you understand why a team skip one measurement to secure another, it feels like watching a good coach manage the clock. You do not need to know every play call. You need to trust that the plays serve the game we said we came to play. By sunrise after a productive night, the newsroom metaphor comes full circle. The map's dimension, the phone's quiet. A headline of sorts takes shape for the internal team. The coma's green strengthened slightly. A new fan appeared on the sunward side. The balance of gases held steady within last week's margin. The tail reacted to a solar gust around midnight. Each sentence is a bead on a string. By itself, each bead is small. Together, they make something you can hold up to the light and show a classroom without apology. And yet the sprint is always running out of road. Each day, the sun moves a little closer to the comet in our sky. Each day, the safe angle shrinks. The newsroom knows the broadcast window will close for a while, and then reopen on the far side with a cooler, quieter scene. Before that happens, we need to be honest about what can slip through our fingers even when we run our best race. That is where we go next, into the list of delicate measurements that will not wait, the kind you only get once if you get them at all. Imagine a field of fireflies on a humid American night. For a breath, they shine, you reach, and by the time your hands close, the little lights have moved. Studying 3i Atlas in these weeks feels like that. The sky offers brief flashes that carry the most important clues, and if we do not catch them in that instant, the dark returns and the chance is gone. We are not chasing spectacle. We are trying to hold steady hands long enough to cup a few living points of light and understand what they mean. The first firefly in this field is a sudden outburst. Comets can spike in brightness as buried pockets of volatile material are exposed. It can happen over hours, and it can fade by morning. Outbursts rearrange the coma, seed the tail with fresh dust, and reveal chemistry that may be hidden in calmer phases. They are also impossible to schedule. A network can watch, but it cannot summon. If an outburst arrives during the worst glare or under a band of cloud, the rise, peak, and decline will be stitched together from half measures. The record will show that something happened without showing how it happened. Jets are the second kind of elusive light. They are narrow plumes that punch through the coma from specific vents on the nucleus. When a jet turns toward the sun, it brightens and throws a fan into the inner glow. When the nucleus rotates, the fan can draw spirals that trace the spin like a signature. Miss the window where a jet faces the right way, and the geometry erases the pattern. See the fan only once, and you cannot tell whether it marks a single crack or a repeating rhythm. These are not trivial details. Jet geometry is the shortest path we have to the shape and spin of a body that we cannot resolve directly. Rotation itself is a quiet, slippery firefly. The way we learn a comet's spin is by watching its light rise and fall with a subtle, repeating beat. A dust-rich side might face us and make the comet a hair brighter, then turn away and dim. If clouds steal one night in a sequence, or if the object dives into twilight too soon, the pattern blurs. A 6-hour period can masquerade as a 12-hour one if the cadence is wrong. Know the period, and you can predict when jets will turn sunward and when outgassing will slacken. Fail to pin it down, and every later measurement floats without a firm frame. There are molecules in the coma that behave like shy fireflies with short fuses. They flare, then self-destruct in sunlight in minutes or hours. Some of them are daughters of larger parents, born in the coma as radiation breaks complex ices into simpler fragments. Catch them, and you gain a direct line to the ingredients locked in the nucleus. Miss them, and the spectrum shows only the sturdier species that linger for days. The difference matters because birth chains reveal both the recipe and the heat of the kitchen. They tell us not just what is there, but how it is being cooked by the sun. Isotopes are the faintest flashes of all. They are the same element with different weights, and their fingerprints in a spectrum sit so close together that a small wobble in the data can smudge them. Yet isotope ratios are among the richest scientific prizes because they carry the climate of the comet's birthplace in their balance. Deuterium to hydrogen in water, carbon-13 to carbon-12 in organics, nitrogen-15 to nitrogen-14 in nitriles. Each pair whispers a temperature and a radiation history. But they require long, quiet exposures when the comet is active enough to be bright and far enough from the sun to be safe to observe. That overlap can be painfully thin. Dust is another kind of messenger that slips away if you are late. The size and shape of grains can be teased from how the coma polarizes light, how colors shift with distance, and how the tail curves under solar pressure. Those signals are strongest when fresh material pours off the nucleus at peak heating. Unfortunately, peak heating aligns with the worst glare in our sky. By the time geometry eases, the stream may have thinned, leaving only the coarser grains that survive the long ride. You can still learn from them, but the portrait is missing the baby powder that says the most about surface texture. There is also the problem of context. The sun blows steady wind, but it also launches gusts and shocks that flex the ion tail like a ribbon in a stadium draft. If a solar gust hits when the comet is near the sun in our sky, only space-based instruments may catch the tail's reply. Ground images taken hours later tell the aftermath, not the story. We can infer the timing from bends and kinks, and sometimes that is enough. But the cleanest lesson is to watch the tail react in the moment. Miss that moment, and the firefly's path is guessed rather than seen. Educational aside, kept short and plain, on how rotation is measured from Earth. When a comet spins, different faces scatter sunlight in different ways. If one face is slightly darker, or if jets add a bit of brightness when a certain region turns sunward, the total light we receive changes. Astronomers make a series of images, measure the brightness in each, and plot brightness versus time. If a pattern repeats with a steady gap between peaks, that gap is the rotation period, or a fraction of it. The trick is cadence. You need enough points over several cycles to prove the repetition and to avoid confusing a day-night observing gap with a signal. It is like listening for a drumbeat while a train passes. You have to separate rhythm from interruption, and you do it by catching enough beats to outvote the noise. There are instrument-specific losses that hurt more than most viewers realize. A spectrograph set to a narrow slit and a particular wavelength band may collect exquisite data on one gas, while letting another drift by. Switching modes takes time and risks losing alignment. On some nights, you gamble for the line that will tell you the most about formation conditions and accept that other lines will go unmeasured. This is not laziness. It is the physics of faint light and the economics of short windows. It is a firefighter choosing which room to open first when the smoke alarm is screaming. My view, stated simply, is that honest uncertainty is not a weakness here. It is a virtue. When we list what we might miss, we are not lowering ambition. We are setting the table so that every measurement we capture is understood in its proper place. I would rather build a modest, robust map than draw a grand mural on shaky numbers. Viewers deserve the same standard. A clear yes, a clear no, and a careful maybe beat a dozen sky-high promises every time. Water is a special case worth its own worry. We rarely see water directly from the ground because Earth's air already carries so much of it. Instead, we watch for a fragment called OH, a byproduct when sunlight splits H2O in the coma. OH glows in ultraviolet light, which is easier to see from space. If those measurements line up with ground-based hints, confidence rises. But if the best window for OH sits inside the geometry squeeze, we may leave perihelion with a debate rather than a consensus. Some teams will argue that the water was abundant. Others will argue the signals were not strong enough to weigh in. Neither is wrong to be cautious. The uncertainty is baked into the timing. There is a parallel in dust. Early dust can be fine and fluffy, loosely bound aggregates that carry the signature of a cold nursery. Later dust can skew coarser as delicate fluff is blown aside or destroyed. Without early polarization and color measurements, we might misread the dust inventory. It is like judging a river by the pebbles left near a bridge after a flood instead of looking at the silt that flowed at the peak. Both tell a story. Only one tells the story you needed most. Another slipping point sits in the nuclear size. We rarely see the nucleus itself when a comet is active. It is hidden in its own glow. To constrain size, we model how much material must be leaving the surface to feed the coma and tail. If we lack peak activity measures because the sun's glare wipes them out, the model must lean harder on assumptions. Later, in quiet phases, you can bound the nucleus with upper limits, but the range may remain wide enough to admit very different physical pictures. In plain terms, a city, a town, or a big stadium could all fit behind the same glow if your only yardsticks are from the wrong week. Coordination can also slip. The gold standard is a spectrum, an image, and a photometric light curve taken nearly at once. That kind of braid lets you tie a chemistry change to a shape change to a pulse in rotation. If one strand goes missing because of weather or scheduling, the knot weakens. You still have parts of the truth, but the cause and effect chain is looser. For normal comets, you can come back next month and try again. For a one-pass visitor, you get whatever the calendar grants. There is a human cost to missing things that we should say out loud. When a line was almost visible and the telescope had to move because of a safety angle, someone carried that decision into the morning. When an outburst started at nautical twilight and there was no safe way to stay on target, a shift of people saw the firefly glow at the edge and then blink out. The right response is not blame. It is to write the night honestly so the next team can plan smarter. America's scale helps and hurts. We have observatories placed to pass the baton, but also weather systems that stall for days. We have space assets with the reach to see ultraviolet and infrared, but with schedules locked months ahead. We have public interest energy that keeps the story alive, but also online noise that can turn a cautious hint into a wild claim in a single headline. What can slip through our fingers is not only a fragile line in a spectrum, it is the thread of trust if we do not narrate losses with the same clarity as we narrate wins. Personal view, again. 2 sentences this time. I think admitting mistakes in real time is part of the craft. People who watch football understand that a drop pass can set up the play that wins the game. They grant grace when they see the team still moving the ball with a plan. There is a final kind of loss that sits outside the telescope dome. It is the loss of context when we fail to connect a measurement to a question that matters. You can announce a rare molecule and forget to explain why a viewer in Indiana or Maine should care. You can stack ratios like pennies and never buy a picture. That kind of slip is avoidable. It happens when we mistake details for meaning. The cure is to tie each fragile firefly to the story it illuminates. A rotation period is not trivia. It sets the stage for chemistry to change with day and night on a world the size of a town. An outburst is not a fireworks show. It is a biopsy, lifting deep material to where light can read it for the first time. The sprint of the last chapter and the catalogue of losses in this one are two sides of the same coin. The speed is not about beating a rival. It is about outpacing the natural fade of signals we may never see again. Humility is not about lowering our gaze. It is about keeping it steady. When you know what can slip through your fingers, you hold differently. You set the net where the fireflies actually fly. Before we move on, we should ask what our past encounters taught us about these fleeting chances. We have seen a visitor discovered too late, and another that stayed long enough to teach us patience. Each left a different kind of hunger in its wake. In the next part, we draw those lessons close and use them to sharpen our choices with 3 atlas, building a standard for evidence that is strict without being joyless. Picture a courtroom at dusk, the windows orange with late light. The judge lifts a hand and reminds everyone that feelings are not evidence. The room grows quiet, and the case resumes with what can be shown, not what can be imagined. That is how I think about our 2 earlier interstellar visitors. One arrived like a rumor that left town before we could check its story. The other stayed long enough to testify, calm and clear. Together, they wrote the rules for how we should meet 3 atlas now. The first guest was a riddle with sharp edges. It flashed through the inner solar system and took the exit ramp before our instruments were warmed up. Shapes were proposed, forces were debated. Even the light curve felt like a trick mirror, stretching our patience and our good sense. There was a temptation to make the gaps themselves into answers. That may be human, but it does not hold up under the weight of time. The durable lesson was simple. When the window is short, humility is a better guide than flourish. The second guest arrived like a neighbor who knocks and stays for coffee. It behaved the way a comet should. It shed dust, glowed in familiar bands, and left a chemical trail that felt like a long letter from a place much like our own solar nursery. Some were disappointed by the lack of drama. I was not. That visit gave us a baseline for what interstellar can look like without mystery piled on top. It taught us that alien does not have to mean strange. Sometimes it means ordinary in a new address. Those 2 visits are now the rails under our feet. We know what happens when you find a thing too late to measure it well. You live with years of speculation and too few checks. You also know what happens when you have time to watch a visitor breathe. Your claims grow steady, and the public can see the picture come into focus without stage lighting. For 3 atlas, we cannot control how long it will stay bright, but we can control our standards. The case for any remarkable claim should fit inside the frame of repeatable measurements. If it does not, it is not a verdict. It is a note to try again tomorrow. My view, offered with respect for both curiosity and care, is that we should be generous with hypotheses and strict with conclusions. Curiosity feeds the questions we ask at the telescope. Discipline guards the sentences we publish in the morning. I would rather be late to a spectacular claim than early to a fragile one that fails a week later. Trust is hard won in science, and it is lost faster than a comet crosses a field of view. The first encounter taught us how space in a dataset can pull ideas toward itself like a vacuum. When the light curve is thin and the shape unresolved, models will multiply. Some will be clever. A few will be beautiful. Most will not survive contact with fresh light. That is not a sin. That is how the process moves forward. The practical lesson for now is to slow our metaphors until the numbers can carry their weight. If a body accelerates a little during its pass, call it a measured deviation first. Save the names for causes until multiple instruments agree on a mechanism. The second encounter taught us the value of patience dressed in ordinary clothes. It gave us water signatures we could trust. It gave us dust that behaved like dust. It gave us a tail that answered to sunlight and wind in the expected ways. That visit put a fence around the word exotic. It told us to keep it in the shed unless the measurements insist we carry it out. For viewers across the United States, that is a comfort. It means a story can matter without a drum roll at every turn. Now we stand between those 2 bookends, with a 3rd volume open on the table. The early hints in 3 atlas point to chemistry worth chasing. There are signs that some ratios may lean in a direction we do not see often. There is that gentle green in the inner coma that announces active carbon. There is a light curve that may hide a rotation we can still catch. Each of these is a promise only if we treat it as a question with a timetable. If one band brightens on a Tuesday, the claim is only strong after Thursday's check. If two instruments agree across different skies, then we can say so in full voice. Educational pause, offered in plain terms. There is a ladder that ideas climb in science. At the bottom is a hunch, the gut-level guess that something might be true. One rung up is a hypothesis, a clear statement that can be tested. Higher up is a model, a picture with numbers that can be compared to what we observe. At the top is a theory, not a guess, but a framework that has survived many tests and explains many things at once. Stories about interstellar comets move along that ladder the same way weather predictions or medical studies do. The right habit is to name which rung we are on when we talk. When we are at the hunch or hypothesis stage, we speak softly and invite checks. When repeated measurements push an idea up the ladder, we let our tone grow firmer, never skipping rungs because we like the view from the top. There is another lesson from those first encounters that matters for how we share updates with the public. We should not punish revision. If a number changes after a better night of data, that is not wobbling. It is refinement. A city planner does not lock in a traffic plan after the first morning commute. They wait a week and adjust the timing on the lights. We owe viewers the same rhythm. Say what changed, explain why, and point to what would help the next step. That is how you make people partners in the process, rather than spectators of a guessing game. Evidence has a posture. It stands straighter when it is seen two ways. In practical terms, an intriguing ratio found in space-based infrared is stronger when a ground-based instrument that measures a different slice of light sees a matching bend. A spike in brightness that looks like a jet's signature becomes a real jet when a spectrum taken at the same minute leans toward the gas that the jet should carry. Those pairings were rare in our first encounter and common in our second. With 3ID Atlas, we should build them on purpose while the geometry still gives us room. The courtroom metaphor holds in one more way. We do not convict on character. Interstellar is not a license for drama. It is a label for origin. The chemistry earns its adjectives the slow way, by showing up in the same place night after night under different eyes. When that happens, the story becomes not only richer but more useful. Teachers can carry it into a class in Ohio or California with confidence. Park rangers can weave it into a night sky talk without having to correct themselves later. That steadiness is worth more than 1,000 gasps. We also owe a debt to the ways those earlier visitors were discussed in public. Headlines can help or hurt. When a claim outruns its footing, a correction rarely catches up. The fix is not to dull our language to grey. The fix is to match excitement to certainty. There is drama enough in the truth. A comet that glows green near the core, because sunlight shakes loose carbon pairs, is beautiful on its own. A ratio that hints at a colder nursery than we expected is a real surprise and needs no costume. If a finding is preliminary, say so and say what would turn it from a maybe to a yes. My personal take is that American audiences reward this balance. People who tune in for space stories want wonder, but they also want to know where the floor is. They do not need us to whisper, and they do not need us to shout. They need us to build a beam they can stand on while they look up. If we do that with 3i Atlas, we can leave them with both memory and understanding when the glare closes in. What do the first guests tell us to prioritize now? They tell us to secure a rotation period if possible, because it solves many puzzles later. They tell us to chase the chemistry that changes fastest while we still can, because late data are kind to slow signals and cruel to quick ones. They tell us to stage instruments so that shape, color, and heartbeat are seen in the same hour. They tell us to write our notes in plain English before the sun comes up, so the next team knows exactly what we tried and what we saw. There is also a deeper habit we can borrow from those histories. It is the habit of archiving with care. When a night ends, the raw files and the calibration frames need a home and a label that will make sense in 6 months. The first encounter taught us that someone will want to reanalyze the light with a new method one day. The second encounter showed how cross-checks depend on clean records. With 3 Atlas, every minute we spend keeping the trail tidy is a gift to our future selves and to the students who will learn this craft by retracing our steps. The first visitor left a bruise in our thinking, a reminder that a thin data set can spark bright theories with little to lean on. The second healed that bruise a little by proving that ordinary comets can come from far away without breaking our models. Together they built a mature stance for this third story. We are allowed to hope for novelty. We are required to prove it. If the ratios push in a new direction after checks and checks again, we will say so with pride. If they fold back toward the familiar, we will say that with equal pride, because a measured no is also a sturdy piece of knowledge. There is a kind of patriotism in this work that has nothing to do with flags and everything to do with shared standards. The United States helped build many of the instruments that are now watching 3I Atlas from the mountains and from orbit. The best way to honor that investment is to treat the data with respect. That means resisting shortcuts, citing uncertainties out loud, and welcoming other teams to test our claims. The night sky does not care which facility got there first. It rewards the village that can read its signals together. The earlier encounters also taught us how quickly a story can tilt when the geometry gets hard. In the first case, the tilt came early and never let up. In the second, the long lead time meant we could surf the curve and land on our feet. For 3I Atlas, the wave is already rising. The sun is advancing in our sky toward the comet's path. The light we want most is stored in the weeks when the glare will be least kind. Knowing that is half the battle. The other half is saying out loud which measurements will be lost if we hesitate, and then moving to catch them now. We should talk plainly about the kinds of claims we will not make unless the evidence demands it. We will not say a chemistry is unprecedented when the yardstick is short. We will not turn an odd evening into a trend without a second evening to match it. We will not dress a noisy line in decisive language. Those are the guardrails the first 2 visitors left us. They are not chains. They are the lines on the road that keep us from drifting into a ditch when the fog rolls in. The most useful part of this chapter is its practical payoff. It sets the bar for what counts as a result in the next few weeks. A result is a measurement that would look the same if another team repeated it under similar conditions. A result is a pattern that holds across instruments. A result is a claim that names its margin of error with the same breath as its mean. Anything less is a hint, and hints are welcome as long as we call them by their right name. Education, one more time in a household, about how a claim becomes solid. Imagine you are baking and a new recipe tells you to use a shorter baking time. You try it once and the center is gooey. You adjust the oven rack and try again. This time it is almost right, but the top darkens too fast. On the third try, you move the pan and tent the loaf with foil for the last minutes. Now it is perfect. If you wrote down each attempt, you could hand the corrected recipe to a friend in another kitchen and expect the same result. That is what repeatability means for comet science. It is not enough that we got a good loaf once. We need to show how to get it again with different pans and ovens. In closing, I will give you my own compass for the days ahead. When I hear a spectacular claim, I ask 3 questions. Did more than one instrument see the same thing? Did the team measure it more than once? Is there a clean explanation for how other effects were ruled out? If 2 answers are no, I wait. If 2 are yes, I lean forward. That habit is not cynicism. It is care for a story that deserves to last longer than a news cycle. Our first encounters handed us caution and confidence in equal measure. They warned us away from the quick thrill of unearned certainty. They encouraged us toward the quiet pride of a well-supported conclusion. With that balance in hand, we can meet 3I Atlas without flinching and without grasping. The courtroom is open again, the witness is on the stand, and the gavel's rule is unchanged. Show us what the light can prove. In the next part, we will shift tone without lowering urgency. We will explain why this story, for all its sprinting, carries no threat to Earth, and how safety and seriousness can share the same sentence as we talk about the value of knowledge for classrooms, families, and the wider culture of science in the United States. Picture a town with two buildings side by side. In one, a firehouse, the red doors are open, and the siren stands ready for the rare day it must wail. In the other, a museum, curators move quietly under steady lights, handling artifacts with white gloves. The firehouse is for danger. The museum is for meaning. The story of 3i Atlas belongs in the museum, not the firehouse. No sirens, no evacuation. But inside, the work is urgent in a different way, because some artifacts do not linger under glass. They pass through, and if you do not study them before they move on, the chance is gone. Let's start with what calm looks like in space terms. The path we have for 3i Atlas is unbound and well-behaved. It cuts through the solar system on a one-time arc that never intersects Earth. The closest approach to our planet will still be farther than the Sun is from us. That is a highway distance in astronomical units, and it is comfortable. There is no hidden turn it can take at the last minute, because gravity works like clockwork. When you know a traveler's speed and direction well enough, you can plot where it will be on any given date, the way a train timetable tells you what platform to stand on. We have that timetable. It points to safety. Safety does not cancel seriousness, though. Seriousness here is the museum side of the street. It is about what the comet carries and how little time we have to read it. Each molecule we detect, each faint pulse in brightness, each fan carved into the coma by a jet, is an artifact from a place we will never visit. These artifacts are not emotions. They are pieces of chemistry and physics that hold the memory of a stellar nursery somewhere else in the galaxy. If you could hold a dust grain from 3i Atlas in your hand, you would be holding a page torn from the first chapter of a planet's origin story, written in a script made of atoms. The United States has always been at its best when it can keep both buildings open at once, when it can assure families that there is no danger while inviting them into the museum to see something rare. That is the tone we earn here. We can tell school districts and city halls that there is nothing to prepare for beyond curiosity, no drills, no budget line for disaster. But we can also tell science teachers and park rangers and anyone who loves a clear night that the next few weeks are a window worth leaning into. If we show up with patience, this visitor can leave our classrooms richer and our imaginations sharper. Some people hear the words interstellar comet and jump to the wrong building. It sounds dramatic, and in an age of quick headlines, drama sells. But good science communication is not a siren. It is a hand on your shoulder guiding you to the right room. It says, here are the boundaries of what we know. Here is what we still need to test, and here is why the test matters to your life, even if you never look through a telescope. That last part is important. Space stories stick when they fold back into our daily sense of how the world works. They shrink the gap between a dark sky in Utah and a kitchen table in Michigan. What, then, makes this story serious if not a threat? The prime candidate is chemistry. Early hints suggest that the balance between common ices may lean a little colder than we see in many comets born near our sun. That kind of lean, if it holds, tells us something about the pantry of elements and temperatures in an alien nursery. It touches questions that reach right into dinner table talk. How often do other systems mix water and carbon early? How common are the raw materials for life? When we speak carefully about ratios and lines and colors, we are not piling on detail for its own sake. We are trying to build the most faithful map we can to the conditions that make habitable worlds possible. And then there is culture. Science is not just a pile of results. It is a way of being public together. When a story like this unfolds in a measured, transparent cadence, the country gets to practice something rare, paying attention without fear. That exercise matters more than we admit. Plenty of issues on the ground would benefit from the same posture, where evidence is shared plainly, revisions are welcomed, and the point is not to score, but to learn. A comet can be a tiny training ground for civic habits. That may sound lofty, but watch what happens when teachers in North Carolina or Oregon put a brightness curve on a projector and ask students to find the pattern. You can feel attention training itself in the right muscles. Educational pause, in everyday language, on why astronomers can say 3-eye atlas is safe without hedging. Space paths obey simple rules. Think of a ball thrown across a field. If you know how hard it was thrown and at what angle, you can tell where it will land. For objects in space, gravity bends the path, but the same principle holds. Astronomers take several precise positions of the comet across multiple nights, fit a curve to those points, and compute how gravity will bend the motion over time. An unbound path means the curve is open, not a loop, so the object will not circle back. When calculations show the closest approach to Earth stays far outside the zone of concern, and when that result holds as more data arrive, the safety verdict is solid. No hidden engine can push a comet off course at the last second. It would show up in the measurements as a steady mismatch, and we do not see that. There is another reason to keep our tone steady. The best way to protect trust is to be picky about words. If we say possible where we mean plausible, if we say confirmed where we mean suggested, we use up the audience's patience before the plot even thickens. I do not think people demand certainty from science. I think they demand honesty about certainty. And when we offer that, they grant us more time and attention than any algorithm could force. In the museum, labels matter. A careful label does not dull wonder. It frames your gaze so you can see the art. My personal view, offered plainly, is that our best role as narrators is to slow down the breath of the story without flattening its heartbeat. We should not douse excitement. We should pace it so the next week has somewhere to go. I also believe the right balance of calm and urgency is a kindness to families who are tuning in with children. It teaches them that grown-ups can talk about big things in clear sentences without reaching for scare or hype. What about the name Interstellar? It is easy to make it a flag. We should keep it a map. Interstellar tells you where the comet came from, not what it will do. It says the ice and dust in this body formed around another star, then drifted through the galactic neighborhood long enough to cross our path. That origin transforms 3 atlas into a delivery, the way a long-lost letter found behind a drawer can tell a family something real about an ancestor. The letter does not change your address. It changes your sense of where you come from and what kin you might have beyond your town. That is the right scale for the heart of this story. Some viewers will ask, wisely, what makes the next week's time sensitive if there is no danger? The answer lands right back in the museum. Light matters. Geometry matters. The signals we need are strongest near the weeks around the closest pass to the sun, exactly when the glare makes observing hardest. That is why we keep using the phrase, closing window. The museum is preparing to hand the artifact to its next stop, which is the dark beyond our reach. We do not panic, we plan. We decide which measurements cannot be done later and give them the best hours we have. The calm is real, so is the clock. To keep all this grounded, here is a kitchen table comparison. Think of a migratory bird that stops in your yard on a long journey. It is not a threat. It will not build a nest on your porch, but it carries a story in its feathers about where it has been and what it ate far away. If you want to learn from it, you walk to the window now, not next month. You get the binoculars and the field guide. You notice the subtle color on the wing. You do not yank open the door and scare it. You stand still and pay attention. That is what serious means in this context. Stand still, pay attention, use the right tools at the right time. There is a role here for the broader American public beyond watching. Communities across the country host star parties, planetarium nights, and park programs. When those gatherings frame this comet as safe but worth your time. They help build a culture that knows how to hold both truths at once. A family that walks out under a dark sky in Wyoming or rural Pennsylvania and hears a park ranger explain what a comet is in 3 quick sentences will carry that clarity home. They might even look up the next clear night and feel the sky as something they share, not as a source of worry. The media can help by keeping the story in proportion. You will not see this channel turn a cautious hint into a certainty for clicks. You also will not hear us bury the lead when a pattern holds across multiple nights and tools. We owe viewers a narrative that breathes the way the science breathes, which is to say, steadily, with its exhale and inhale labeled for what they are. Here is what we saw. Here is what it might mean. Here is what we are doing next, to find out if they might harden into it. Another serious dimension has nothing to do with telescopes. It has to do with students. A well-told comet story can change the trajectory of a teenager in Detroit or Phoenix who has never felt invited into science. When they see careful work done in public, without gatekeeping, with clear language and open data where possible, they learn that science is not only a subject. It is a posture available to them. If this series plants even one such seed, that is a return any grant officer would envy. We should also admit that a safe but serious story can feel strange in a feed tuned to extremes. That is all the more reason to tell it. The world will always supply sirens. We should get better at building museums where the lighting is steady and the labels are honest. 3i Atlas gives us a chance to practice. We can tell you what matters without scaring you. We can frame urgency without breathlessness. We can praise skepticism without turning it into cynicism. That balance is hard and worth the effort. One last educational loop, short and simple, on why certain colors in a comet's light have captured so much attention without implying risk. When sunlight hits gases in the coma, those gases can glow in specific colors. Green often points to pairs of carbon atoms excited by light, which tells us that carbon-rich material is being processed in the shell around the nucleus. Blue can signal charged molecules in a tail swept by the solar wind. These colors are like highlighters on a page. They tell us which lines to read more closely. They do not signal hazard. The glow is thin and distant, a tracer of chemistry, not a threat. My view in closing is that the safest, strongest stories are the ones that keep their feet on the ground and their eyes on the sky at the same time. We can walk and look. We can reassure and still care. The museum can hum while the firehouse sleeps. If we do this well, we will end the season with better maps of how planets begin, a few new young scientists setting out on that path, and a public that remembers how good it feels to learn without being told to be afraid. The next step in our tour of the museum is to walk closer to the exhibit itself. We have talked about safety and tone. Now we will lift the veil on the artifact. In the next part, we open the snowball and examine the layers of ice, dust, and gas. Using simple metaphors you can taste and touch to understand how ingredients and temperatures shape a world that formed under a different star. Think of a layered cake kept too long in a deep freezer. The frosting has dried into a thin shell. Inside, pockets of sugar and air sit between dense, cold crumb. Bring it into a warm kitchen, and the top sweats, the shell cracks, and sweet steam escapes through the hairline faults. That is the working picture of 3i Atlas, a crust hardened by eons in the dark. A porous interior laced with ice and dust. Heat from the sun moves in like afternoon through a window, shallow at first, then deeper, reshaping what can escape and what must hold. Start with the core, the nucleus, because everything we see comes from there, even if we never see it bare. It is small on planetary scales, likely measured in fractions of a mile to a few miles across, but it is a world to itself. The surface is not glossy. It is more like a driveway after a long winter, patched and rough, with pebbles set in brittle cement. In the cold, gases froze among these grains. Now, touched by sunlight, those ices begin to lift. Gas threads through the pores. nudges dust free, and builds the coma that makes a comet look alive. We read that the coma is a mirror of the interior, a messenger speaking for the hidden core. The crust forms because comets are poor at keeping their shine. Fresh ice near the surface sublimates first, leaving behind dust that settles into a blanket a few inches to a few feet thick. That blanket changes how the next day's heat sinks in. It can clog vents. It can redirect the breath of the nucleus toward weak seams. Where the blanket is thin, jets can punch through and fan the coma with narrow sprays. Where it is thick, the surface looks dead, even while the interior boils softly. The pattern of active and quiet patches is the first handwriting we try to decode. Inside the crust, the material is not uniform. Think back to our cake. Some slices hold little cavities where bubbles once lived. Other slices are compact. In a comet, those differences show up as light and heavy pockets of dust and as ices with different temperaments. Water ice wants one level of heat to let go. Carbon dioxide and carbon monoxide want another. Salt the mix with a pinch of organics, and you have a pantry that responds to the sun in stages. Early on, the quick-to-flee species dominate. Later, as heat creeps farther in, even stubborn water joins the flow. We watch the timing in the light, and from that timing, we sketch the layers. The green glow we keep mentioning lives in the first few thousand miles around the nucleus, a kind of sea glass sheen where carbon pairs flash as sunlight tickles them. It does not tell us that the nucleus itself is green. It tells us that carbon-rich materials are being processed on the fly, broken and recombined in the thin air of the coma. That inner shell becomes a workshop. The sun is the lamp. Chemistry is the set of tools. If the glow brightens or fades from night to night, it hints at how steady the workshop line is, or whether a new seam has opened to feed it. Dust deserves its own look, because it carries a history that rocks alone cannot. Some grains are fluffy aggregates, like the lint you shake from a dryer screen. Those form in cold packs and fall apart easily. Others are more compact, closer to beach sand. When a comet is at peak activity, it throws both. The smallest specks move fastest under sunlight's push, curving the dust tail like a long streamer. Larger grains lag and chart a different arc. By measuring color and polarization in the coma, we gauge the mix of grain sizes and shapes. It is a kind of forensics. The dust tells us whether the surface was coated in powder or patched by gravel, whether the grains were freshly exposed or already baked once and densified. We also look for hints of how the interior holds together. Some comets behave as if they are single blocks. Others seem more like loose piles, rubble bound by gravity and cold. In a loose pile, gas can take many paths to the surface. In a more solid core, a few cracks carry most of the load, and jets show up as sharp features. One way to tell the difference is to watch how the nucleus reacts to its own outgassing. When gas vents from one side, it pushes back a little, like a hose nudging a person holding it. Over many days, that push can alter the spin slightly. If the rotation changes in step with activity, we learn about both the strength of the core and the structure of the vents. Heat does not march in all at once. It fades with depth. Engineers call the reach of a day's warmth the skin depth, the depth where the daily temperature wave still matters. For a small body, that depth can be measured in inches or feet. Below that, the interior may remain at interstellar cold even as the surface hisses. That means the cake stays mostly frozen while the frosting melts. Why should we care? Because the relative calm of the deep interior preserves the oldest record. Only the thin, sun-touched layer is edited by this passage through our system. If we can separate the voice of the skin from the voice of the core in the data, we can aim our inferences at the right chapter of the story. Ratios between gases are our best compasses. They steer us toward the nursery, where this comet began. A higher share of carbon dioxide compared to water, if it endures across multiple nights and instruments, suggests formation in a colder region of a disk, where carbon dioxide could settle and stay. A more water-heavy mix points closer to the warmer belt where our own frost line sat. These are not mere labels. They are weather reports from a different star's childhood, fossilized in ice and read out by light. When a ratio looks unusual for the comet's distance from the sun, our ears perk up. The question becomes whether that odd lean holds when measured again and again, and whether the green we see in the coma rises in step with it or follows its own rhythm. Here is a kitchen counter education moment on volatile ratios, kept short and clear. Imagine two kinds of ice cubes in your freezer. One is made from water. It melts on a summer afternoon and leaves rings under your glass. The other is made from club soda. Leave both on the porch. The club soda cube does two things sooner. It fizzes and it shrinks even before it melts into a puddle, because the gas trapped inside wants out as soon as it warms a little. In a comet, water and carbon dioxide behave a bit like those two cubes, though nothing really melts into a pool in the vacuum of space. Instead, each ice has a temperature at which it is more eager to turn into a gas. If the mix has more of the eager kind, you will see signals tied to that species earlier and stronger. Measuring how those signals change as the comet warms tells you how many club soda cubes the baker used in the cake, and whether the freezer where it formed was set to a different temperature than ours. Isotopes push deeper into origin. These are the same elements at different weights, little taggers attached to the atoms. The balance between heavy and light in water, carbon and nitrogen acts like a faint tattoo from the comet's birth environment. Colder clouds leave one balance, warmer zones leave another. We are cautious here because the lines are delicate and can be smudged by noise. Still, when the exposure is long and the activity is high enough, those tiny spacings in the spectrum can be read. If we can read them for 3-item atlas, we gain not just a neighborhood on someone else's map, but a climate. There is a place where geology and chemistry meet, and it lives in the structure of jets and fans. A narrow jet suggests a vent cut through the crust, a chimney with a stubborn cork that pops now and then. A broad fan suggests a larger weak patch where gas seeps through many pores at once. If a jet pulses with the rotation period, we can tag it to a specific longitude on the nucleus. If a fan grows brighter when a certain region faces the sun, we have found a province. Over time, these repeated patterns let us sketch a rough map, a dusty plateau here, a volatile rich seam there, a block of material that resists warming over there. We are map makers working by inference, drafting from the wind rather than from photographs. My personal view, offered without ornaments, is that this interior portrait earns respect because it is humble. We do not pretend to peel the shell with our eyes. We accept that a veil lies between our instruments and the source, and we build our case from echoes. I think that kind of science is beautiful. It asks for patience, invites checks, and grows stronger every time a new instrument says the same thing differently. I also think we should resist turning one odd ratio into a sweeping headline about alien chemistry before that patience has run its course. The birthplace question reaches beyond one star. If a comet like this, formed in a disk, richer in carbon relative to oxygen than ours, the mix of ices and organics would tilt toward different recipes. That matters for more than comet trivia. Comets deliver seeds. On young worlds, they can carry water and carbon chains. The balance they bring tips the chemistry of early oceans and soils. So when we draw arrows from a ratio to a nursery, we are also drawing lines from a nursery to the odds that certain planets in that system started wet or dry, rich in certain building blocks or poor. This is not a shortcut to life questions. It is a way to keep those questions anchored while we wait for better tools. Dust again, because so much of a comet's voice is in its powder. The grains reflect light unevenly, depending on size, shape, and composition. By catching how the coma polarizes light at different angles, we can estimate whether the grains are more like soot or more like tiny snowflakes. If the near-nucleus region shows a steep change in polarization with distance, it may signal fragile clumps breaking apart, leaving behind smaller, brighter specks. That tells us the surface layers were loosely held, a sign of youth for that patch, even if the comet itself is ancient. In contrast, a flatter polarization curve hints at grains that have already been through a heat and cool cycle, fused a bit at the edges, and learned how to hold together. Size and density lurk behind many of these inferences. A smaller nucleus with the same level of activity as a larger one needs stronger vents or more volatile, rich pockets to keep up the flow. A lighter, fluffier body will respond more to its own outgassing, showing subtle changes in spin or path. A denser, tougher core will shrug off those pushes. We do not pull these numbers out of thin air. We build ranges by matching how fast the coma must be fed to how wide it looks and how bright it glows, and we test those ranges against how the coma's shape evolves under solar wind gusts. Each test tightens the frame a little more. Cracking and healing are part of the life of a sunlit comet. As heat crawls in and gas leaves, the top layer can slump and split. A crack that opens one afternoon can seal again as dust falls back and plugs the gap. Over days, these small shifts sculpt pits, ridges, and ledges. We know this not from 3i Atlas directly, but from missions that are flown by other comets. Those images gave us a vocabulary of surface types: smooth ponds of dust, broken cliffs, dark caps. With that vocabulary, we translate 3i Atlas's light into plausible features without pretending we have a portrait. The better the translation, the more accurate our map of the interior's pathways. There is a thermos quality to the deeper layers. Even when the outer inches get lively, the core can stay at a steady cold. That means some materials we see later in the passage are seeing sunlight for the first time in ages. A late rise in a particular line may not mean the comet was born rich in that species. It may mean the wave of warmth has finally reached a vein that held it. Timing again becomes a compass. If the green brightens before water clues grow strong, that suggests a certain ordering of layers near the surface. If water clues come early and the green lags, the layering is different. Either way, the order matters more than the headline color. Educational sidebar 2, in simple weather terms, about skin depth and why timing tells us about layers. Imagine a hot summer day in Texas and a concrete porch. At noon, the top is too warm to touch. An inch down, it is cooler. 6 inches down, it still feels like morning. Sunlight's heat does not penetrate all at once. It rides a wave into the material and fades as it goes. In a comet, the daily wave and the seasonal wave both play. The first affects inches, the second can creep deeper. When we watch which gases rise first and which rise later, we are reading those waves like a thermometer buried at different depths. That is how the sequence of chemistry becomes a map of layers without any digging. I have learned to love this style of detective work. It rewards steadiness. It refuses to be rushed. It keeps your claims bound to what the light can support. As a narrator, I am drawn to that ethic because it respects the audience. You do not need surprises every minute. You need clarity you can carry back to your life and recall a week later. The layered cake metaphor is not just a picture. It is a reminder that, like good baking, good science is about temperature, time, and texture, repeated carefully until the recipe holds. All of this interior talk leads to a practical point. To know the inside better, we must keep watching the outside under harder conditions. The sun is rising in our sky toward the comet's course. The glare is growing. Our measurements in the days ahead will be made at smaller angles and shorter windows. That is why the geometry of the next stretch matters as much as the chemistry. We are trying to read a snow globe held close to a spotlight without blinding ourselves or cracking the glass. In the next part, we will step out of the kitchen and onto the playing field of angles, light, and safety. We will explain why comets become hardest to study right when they are most alive, and how careful planning keeps telescopes from looking too close to the sun, even when the best science sits on that bright edge. Picture a center fielder under stadium lights at dusk. A flyball rockets straight up, and for a heartbeat, the player loses it in the glow. The ball is the comet. The lights are the sun. We know where the ball is headed. We also know that looking straight into brilliance, even for a moment, is how you miss the catch. Studying 3 Atlas as it slides sunward is the same kind of play. The closer it gets to the spotlight of our star, the brighter the backdrop and the harder the track. From Earth, the comet is not physically touching the sun, of course. The trouble is optical, not orbital. As Atlas approaches its closest distance to the sun, it appears nearer to the sun in our sky. That shrinking separation squeezes the safe lane for telescopes. Sky glow swells. Scattered light floods detectors. Instruments that happily dig faint signals out of black velvet must now pick a whisper out of a brass band. Ground observatories live by angles. Most professional telescopes keep a strict buffer from the sun, a keep-out zone that protects sensors and optics. Even far from that safety line, you still fight a rising background. Twilight eats the faintest detail. Air near the horizon is thicker and dirtier, bending and blurring light. Add a thin wash of moonlight or a run of wildfire smoke, and the faint green close to the comet's core gets drowned in a smear of grey. The geometry has a second trick. As the comet drops toward the sun in our sky, it hugs the same slice of evening or morning you do when you drive straight into sunset on an interstate. Your eyes strain, the road's texture vanishes, and you grip the wheel a little tighter. Even with sunglasses, contrast collapses. Telescopes feel that collapse. They can shorten exposures, switch to filters that cut unwanted glow, and time shots to the darkest few minutes. But every workaround costs something. Shorter exposures mean fewer photons. Narrower filters mean a smaller piece of the spectrum. Less time at night means fewer attempts to catch the comet steady between gusts of air. Space telescopes help, but they are not all-powerful. They also respect sun angles to keep their instruments safe and their temperatures stable. One observatory can look closer to the sun than another, but none can stare right along the glare line. In practice, that turns into a schedule shaped by safe pointing windows. The best chemistry sometimes lands just inside a period when a platform is required to look away. You feel that pinch, like a chef who knows peak tomato season is this week, yet has to use tomorrow's lunch shift to prep the pantry. A second bit of geometry, less flashy but just as stubborn, is phase angle. That is the angle between the sun, the comet, and us. When the angle grows wide, dust can scatter sunlight forward toward us more efficiently, and the coma seems to shine a little more. But the same angle that boosts the glow often happens when the comet is low and the background is bright. We end up with a paradox. The comet is technically brighter, yet practically harder. Astronomers thread that needle by choosing moments when the phase is helpful, but the sky is still dark enough to matter. Educational break, in simple terms, on solar elongation and why it rules our plans. Think of the sky as a giant clock with the sun at the center. The elongation of a target is like how many minutes it sits away from the sun on that clock face. Big elongation means the target is well separated and the sky around it is dark. Small elongation means it hugs the sun and the sky is full of glare. Telescopes draw a circle around the sun on that clock and vow never to look inside it. The exact size of the circle varies by instrument, but the idea is the same. Stay outside, and you protect hardware and keep your images from being washed out. When the comet's path carries it toward the edge of that circle, your nightly window shrinks. You do not stop caring. You change tactics and prepare to pick up the object again once it walks back out into the dark. Timing gets more surgical as the angles close. Teams strip their sequences down to essentials. A filter set that once took an hour gets boiled to 20 minutes. A wide scan becomes a tight shot at the exact spot where the comet will be when the sky is darkest, often just before dawn or just after dusk. You can picture the workflow like a high school football coach practicing 2-minute drills all week. Every motion is logged. Every swap of camera mode has a checklist. The aim is to bank clean minutes while the sun is still behind the bleachers. Even the way the atmosphere steers light matters now. When a target sits low, The path through the air is long. Heat ripples, wind shear, and tiny layers of temperature difference stack up to scramble the sharpness. Observers compensate by planning the longest exposures for the moment when the comet crosses its highest point, even if that moment comes with only a thin border of darkness around it. They anticipate the angle the object takes across the sky to keep the coma centered on the slit of a spectrograph. They pre-program telescope tracks to follow the comet's motion so the tail does not smear into the background. Moonlight is a geometry problem too. A bright moon sitting across the sky from the comet spreads its own wash of grey, raising the baseline and thinning contrast. A moon near the comet is worse. A floodlight behind your flyball. You can plan around the moon. You cannot move it. That makes the waning crescent a friend and the gibbous phase a foe. In weeks like these, lunar calendars share desk space with comet ephemerides. If a narrow window of darkness lands on a moonless hour, you use it. If not, you aim for lines in the spectrum that rise taller above the background. Space offers alternate vantage points that can blunt geometry's elbow. A spacecraft near Mars, a solar observatory parked off Earth's line, or a mission on the far side of our planet's orbit might look at Atlas from a different angle, safe from the glare that blinds us. Those assets were not built for comets, but sometimes they can help. Even a modest image from a second seat in the stadium can confirm a jet or a sudden fan in the coma when Earth-based scopes are off the field. Parallax between viewpoints can sharpen size estimates and trace the three-dimensional shape of the tail. No single vantage point solves everything. Enough of them together turn a flat map into a globe you can spin. Our craft also assigns risk honestly. A telescope is not just glass and steel. It is a community's memory. Pointing too near the sun is out of the question. Even longer exposures with a safe margin carry a different kind of risk as glare rises. Faint lines can be faked by imperfect subtraction of the sky. Fine structures can be etched by the way light scatters inside an instrument. That is why teams build flats, darks, and careful models of how their cameras behave when the background is bright. They correct, then check their correction with calibration stars, then check again. The closer we get to the edge, the more often the crew asks out loud, "Does this survive a second look?" You feel the same discipline in how they decide between imaging and spectroscopy. A wide-field image captured in perfect seeing can freeze a jet. A deep spectrum gathered under a bright background might still recover a faint line that says carbon dioxide is active. In the geometry squeeze, you rarely get both on the same night. The choice is strategic. If morphology is changing quickly, the image wins. If chemistry is the only way to test a hypothesis from last week, the spectrum wins. When space can give one, while ground takes the other, the plan splits. When both are out of reach, the plan pauses and shifts effort to post-sunrise reduction, so the first clean hour tomorrow is spent smarter. There is a plain truth here that is easy to miss. The comet is most alive when we are least able to watch it. Solar heating peaks. Jets wake. Dust and gas flow at their fastest. That is also when the sky is brightest along the line of sight, and the safety rings around the sun press in tightest. The paradox is old, and it will be here for the next interstellar visitor. Our job is not to beat it. Our job is to sidestep it with timing, teamwork, and the patience to resume the watch on the far side. On the far side is where reacquisition lives. After the sun has marched past the comet in our sky, the angles widen again. The object reappears in a darker wedge of dusk or dawn. It is fainter, yes, but calmer geometry gives back what brightness took. Teams plan now for that return. They simulate how the tail might look if an outburst occurred in the bright gap. They have ready search patterns to find the comet quickly, even if it behaves a little differently than predicted. In practical terms, that means booking time on nimble telescopes for the first week of visibility and reserving deeper nights a week later if early checks land well. Amateurs help here more than they are often credited. A backyard telescope in a dark corner of Kansas or Vermont can pick up the returning smear before a big facility can schedule a slot. Those images, carefully logged with time and location, add dots to the path that keep ephemerides tight. They can also flag surprises, a kink in the tail, a sudden fan, a brightness bump. The geometry may have eased, but the story has not ended. A community that shares images well, with notes and context, makes everyone faster. My personal view is that geometry is where patience stops being a virtue and becomes a skill. Anyone can wait. Few can plan the waiting, so the first minute back on target is the one that counts. I have enormous respect for the crews who hold that line. They refuse the drama of unsafe angles. They also refuse despair. They keep their tools sharp, their schedules nimble, and their claims modest until the sky invites them back. There is one more nuance worth naming because it shapes how we talk to you about the next 2 weeks. When geometry batters data, uncertainties grow. You will hear us use more careful words. You will see us move from nightly pronouncements to patterns shown across several nights. That is not retreat. It is the right speed under bright lights. The reward is a story that still stands a month from now when Atlas emerges into a cleaner sky. And we ask, did the coma's green act the way the geometry-limited week suggested? Or did we misread a glare artifact as chemistry? We cannot answer that if we overstate the bright-edge data now. In practice, the geometry problem forces a pivot in how the team assigns value. Before the squeeze, a marginal detection can be worth chasing because a second chance is likely tomorrow. In the squeeze, a marginal detection is put in a holding pattern unless it bears directly on a decision about the next night's plan. That discipline keeps us from spinning our wheels in bright sand. It saves time for reductions of the most solvable questions, like whether a suspected rotation period is consistent with the latest light curve, or whether a dust fan moved in a way that matches the solar wind's behavior that day. If all of this sounds like the coach's manual for a 2-week road stretch, it is. Long nights, quiet discipline, short bursts when the lane opens. The spectacle is still there. It is just behind the glass of good habits. The best news is that the geometry problem, as unforgiving as it is, does not last. The sun moves on. The dark returns. The comet survives the glare. We will be waiting with better questions and a tighter plan. And if you find yourself thinking, could we skip the lights entirely and run to the ball? You are not alone. The geometry problem tempts you toward the next chapter. If we cannot always see clearly from here, why not go there? Why not send a craft to meet the comet where glare cannot bully us? The answer is a lesson in speed, fuel, and planning. That is where we turn next, to why this time we will not catch 3i Atlas up close, and how the right kind of preparation makes a different answer possible for the next hello. Picture a freight train roaring through a prairie crossing at midnight. You stand by the rails with a flashlight and a notebook. You can see the cars, count the containers, even spot markings as they blur by. But there is no honest way to jump aboard. If you truly wanted to ride that train, you would have staged miles down the line with a locomotive idling and a crew strapped in, departure order signed and sealed. That is our situation with 3-eyed Atlas. The train is real, the speed is breathtaking, and the crossing is right in front of us. We can study, we cannot hop. Catching a comet is not the same as pointing a camera. Cameras can pivot in seconds. Spacecraft are slow promises. To meet 3i's Atlas up close, a probe would have to do 2 hard things. First, reach the spot in space where the comet will be. Second, and more difficult, match the comet's speed enough that the meeting lasts long enough to work. Crossing a track is simple. Pacing a train is hard. The comet's path is a one-time arc, a door that swings through the inner solar system and closes. That arc is steep, the speed high, and the discovery came late in mission years, even if it feels early in news days. In spaceflight, the currency is the change of speed. Engineers call it the budget you spend to speed up, slow down, and steer. The larger the budget, the bigger the fuel tank or the smarter the trajectory. Slow, efficient engines can squeeze more miles out of a small tank, but they need weeks and months to do their work. Fast, muscular engines are quick, but they drink fuel. Either way, you pay. For a hyper-fast visitor on a one-time track, the ticket price is beyond what we have in hand. You would need a launcher ready on the pad, a spacecraft fueled and checked, instruments tested against the chill and radiation of deep space, and a flight plan validated. Those pieces do not assemble between press conferences. A rendezvous is not a cinematic flyby. The difference is the difference between waving at a marathoner from the sidewalk and running alongside to ask questions. A flyby can collect a handful of images and spectra in minutes as it whips past. A rendezvous slows the spacecraft enough that the instruments can watch the same features turn, breathe, and change. To slow in that way, you either start early with efficient thrust, or you carry a mountain of fuel to burn in a hurry. We have neither for this object. It is not a lack of imagination, it is a lack of a calendar. Launch windows are another quiet gate. The Earth spins, it orbits the Sun. The target moves on its own path. Those motions make a moving puzzle where certain days open a lane and other days lock it. Even if a spacecraft was somehow ready in record time, the right lane might not align with the days when the pad is free, the weather is safe, and the tracking network can pick up the signal. Spaceflight is not pizza delivery. It is a convoy that needs permits, refueling points, and open highways, all synchronized. Think about this in terms closer to home. A family in Ohio can order a paperback on a Tuesday morning and see it on the stoop by Wednesday because millions of dollars have already been spent on warehouses, trucks, software, and routes. That speed is not created on the day you click. It is made beforehand by staging. Space is the same. If we want to intercept the next interstellar visitor, we must build the warehouse now, stock it, and keep the engines warm. That is the thinking behind standby missions that wait in a quiet neighborhood of space, ready to sprint when a target appears. For 3i Atlas, that warehouse is not open yet. What about repurposing something in flight? It is a fair question. Deep space is not empty of our machines. Could we bend the path of a spacecraft already working near a planet and send it to meet Atlas? The answer is almost always no, for 4 sober reasons. The first is fuel. Orbiters carry enough to do the job they were built for, with a margin for safety. A new chase would burn that margin, and then some. The second is hardware. Cameras and spectrometers are tuned for their worlds. A Jupiter probe is optimized for clouds and fields, not for a small, fast snowball in sunlight. The third is time. Planning a safe departure from a planet's gravity and targeting a new object takes months of modeling and rehearsal, if it is possible at all. The fourth is trade-offs. Ending a primary mission to pursue a long shot is not free. It is a choice to retire a sure stream of discoveries for a gamble that may pass the station in the night too dim to see well. Educational aside, short and plain, on why the change of speed rules everything. Imagine you are biking down a long hill. To join a friend riding ahead at the same pace, you do not just swerve into their lane. You must match speed. If you are slower, you sprint. If you are faster, you brake. On an easy bike. In space, braking and sprinting are costly. To speed up or slow down, a spacecraft throws mass in one direction so it can change speed in the other. The faster you want to change, the more mass you must throw. That mass is fuel, and it is heavy. The trick is that hauling extra fuel means you are heavier to begin with, so you need even more to push yourself and your fuel. This is why missions try to start early, take gentle paths, and use a planet's gravity to bend their way. They save their precious change of speed for the moments that matter. When a comet is found only months before the best encounter, there is not enough time to build a gentle path to the train, and the heavy sprint is beyond what we can lift. We should talk straight about shiny ideas that sometimes float by when a story like this hits the public square. Could a giant new rocket dash after the comet? Could we strap a small probe onto a powerful booster and improvise? The limits are not only about thrust, they are about reliability. Flying untested systems toward a one-time target is a recipe for heartbreak. Even a tested system needs time to integrate the payload. Check out the instruments in the chill and vacuum of space, and prove that the communication and guidance work end to end. Those steps are not bureaucratic drag. They are seatbelts. Without them, you do not get science. You get a souvenir list of what you should have done. Another bright idea is a sail pushed by sunlight. It is elegant and efficient once deployed, but it starts slowly and rewards long lead times. Ion engines are similar. They sip fuel and build speed with patience. They excel when you have months to accelerate, not weeks. Nuclear thermal engines promise higher performance than chemical rockets one day, but they do not exist as a mission-ready option yet. Even if they did, the careful testing and safety reviews such a system deserves would take longer than the weeks we have. Notice the pattern. Every fast option is slow to prepare. Every slow option needs time to work. The only answer that flips the table is prepositioning. Build, launch, and wait in a stable spot, with fuel on board, sensors warm, and a plan to pivot when a visitor appears. In practical terms, that means parking a small fleet near a balance point where the sun and earth pull equally and where communication is clean. When the alert sounds, the fleet tips a little gas, glides onto the train's track, and meets the visitor with enough time in hand to do more than wave. This is where my own view is simple. Not catching 3i Atlas is not a failure. It is a reminder. Space rewards those who prepare. In my opinion, we should invest in the boring parts of readiness. The checkout lists, the spare parts, the fuel margins, the craft that can idle safely for years without losing its edge. I also believe we owe the public clear reasons for these choices. The same patience required to do it right in space is one we can model in how we tell the story. We do not need to promise stunts. We need to prove we can keep promises. The limits on chasing this comet are not only about rockets, they are about knowledge. When you build a mission to meet a specific target, you tune your instruments to the lines you expect to see, and you shape your flight plan to give those instruments the best light. For a visitor found months before the bright season, you do not have enough evenings to analyze its early spectra, test your filters, and update your exposure plans. You would be boarding a plane with the wrong lens on your camera and no bag of backups. That is not how you collect history. Another constraint is navigation. Meeting a small, fast object in deep space is like docking a canoe with a leaf in a river. You need precise positions, not once, but night after night, so your craft can correct its aim. Those positions come from a chain of ground and space observations that themselves take time to gather, process, and feed back into the plan. The chain can be quick. It cannot be instantaneous. That lag matters most when the target is accelerating through the inner system. By the time you have the lane locked, the train has already passed your exit. Consider also the network that talks to the spacecraft. Big dishes spread around the world listen for weak whispers from probes across the solar system. Those dishes have their own schedules. They serve many missions that span years. They can fit in a short campaign in a crisis, but they cannot devote months of around-the-clock coverage to a new chase without reshuffling a dozen other plans. You do not launch a mission if you cannot guarantee a line of communication. For 3 Atlas, the schedule you would need simply does not exist on that timescale. There is a humbler truth hidden in these limits. The best science does not always come from touching. Remote sensing done well is not a consolation prize. It is a craft with its own rigor. We stand at the crossing as the train passes because that is the safe place to stand, and we pour everything we have into counting, measuring, and reading each streak of light. What we lose in intimacy, we make up for in coverage. The comet is larger than any one vent or boulder. The big picture needs a web of telescopes collecting over weeks with different angles and colors. We can build that web now. We are building it now. I feel a responsibility to connect this to the American habit of solving hard problems by building systems that last. When hurricanes threaten a coast, we do not invent a new kind of truck. We pre-position supplies and crews. When the holiday rush strains a delivery network, we do not promise to lift boxes faster by hand. We shift routes, lease extra vehicles, and staff overtime. It is the same here. The way to answer the public desire to get closer is to build the quiet, expensive, unglamorous capacity to respond. It is to keep a spacecraft or three in the cosmic equivalent of a firehouse, fueled and ready. There is a final reason we will not chase 3i Atlas with a last-minute plan. It is respect for the missions already flying. The teams behind those crafts have dedicated years to their targets. Diverting a healthy mission away from its promised science to try for a risky encounter would break trust and return little. The better move is to ask those missions for a gift they can afford. A quick look from a different angle. A set of images that confirms a feature seen from Earth. A cross-check on a color that might be chemistry. Those are realistic asks, and they matter. They will show up in our maps of this comet with the same weight as any glamorous attempt to sprint. All of this sets up the right kind of ambition for the near future. We cannot catch this one, but we can chase shadows in useful ways. We can convert a Mars orbiter into a witness for a week. We can lean on solar missions for off-angle views of the tail. We can empower amateur observers across the United States to pick up the returning glow as the geometry eases after the bright gap. Each small vantage point fills a hole the glare would leave. That is a grown-up way to add value when the main door is closed. The practical takeaway is that strategy beats stunts. For the next interstellar, hello, we should launch early, wait smart, and share fast. That means survey telescopes that find visitors at the edge of the map. It means standby probes with cameras and spectrometers that can pivot. It means data standards that let ground and space braid their results overnight. It means education that tells this story without promising what physics and calendars will not allow. Done right, the next crossing can be a platform, not a fence. We end this chapter where we began. At the rails in the American dark, the train thunders past. We watch with steady hands. We learn from the blur. We do not leap. There is honor in that choice. The notebook we fill will still matter the morning after, and the engines we build for next time will idle in a place where the sprint can begin before the horn. From here, it is natural to ask what smaller doors are still ajar. If we cannot board the train, can we at least climb a hill to see the cars better? Are there short windows, side angles, and clever vantage points we can borrow to add detail while the glare grows and fades? In the next part, we open that playbook, looking for opportunistic views that trade perfectly for possible and still move the story forward. Imagine a theatre with the main curtain drawn and only the side doors cracked open. You cannot see the whole stage, but if you lean at the right angle, you catch reflections in a mirror, hear a singer warming up, and glimpse a dancer in profile. 3i Atlas is performing under the brightest spotlight in the sky, and the house lights are against us. That does not mean the show is over. It means we work the side doors. We look for balcony seats, hallway mirrors, and narrow aisles that let a careful audience gather enough to understand the scene. Opportunistic windows are those side doors. They are short, sometimes awkward, often risky, and they matter. The point is not to replace the grand plan. The point is to stitch together what the grand plan cannot reach while the glare is highest. Some windows require nothing more than redesigned checklists at ground telescopes. Others ask spacecraft teams to tilt cameras away from their usual subjects for a brief look. Each one is a trade, a little risk for a little gain. Stack enough of those gains, and you turn a thin week into a story that still holds. Start with a different horizon. Earth is one seat in the theatre. Mars is another. When a comet passes closer to our red neighbour than to us, orbiters there can become ushers for a night, guiding us to a better angle. A camera meant to map ice caps or dust storms can, with careful planning, be pointed outward for a narrow campaign. The view will not be cinematic. The instruments were not designed for stars and comets. But even a modest series of images taken from a second perch can do two big things. It can confirm a feature that Earth-based teams only half saw through glare, and it can pin down size and structure through parallax, the same way two eyes reveal depth. Solar sentries offer another window. Spacecraft that live to watch the sun carry coronagraphs, clever instruments that block the disk of our star so the faint corona around it can be seen. Comets that swing near the sun sometimes drift through those fields of view. The geometry is not always kind, but when it is, a comet can be tracked as it skirts the edge of the blocked region. The images are grainier than what large observatories produce at night. Their gift is not fineness, it is continuity. While ground telescopes step back to respect safety angles, a solar sentinel can keep watch and record the broad shape of the tail, the timing of any outburst, and the overall brightness curve through the worst of the glare. On Earth, twilight is not dead time if you plan for it. The sky is bright, but it is also brief. Observers can carve science out of those minutes by choosing questions that fit inside them. Broadband images to capture tail curvature. Short spectroscopic peaks at a single well-isolated line. Polarization snapshots that say something about dust without demanding long exposures. It is a different rhythm, like running interval sprints instead of a mile. Done right, the sprints add up. They give the night's main observation a frame. This is how the coma was evolving before dark. And this is where it landed once true night arrived. Shadows offer their own side door in the form of occultations. When a comet passes in front of a star, the star's light dips for seconds or minutes. That dip can reveal the size and shape of the solid nucleus far better than any blurred image. The trick is that occultations are needles in a hayfield. Prediction requires good ephemerides and luck. Catching one demands a band of observers spread across the path with synchronized clocks. In return, you get a direct constraint on the part of the comet we rarely resolve. If Atlas cooperates, and an occultation crosses North America at a safe hour, citizen astronomers from Texas to the Dakotas can take part in a measurement usually reserved for spacecraft. High in the air, there are quiet platforms we underuse in stories. Weather balloons can loft instruments above most of the haze. Their payloads are light, but they can carry cameras and small spectrographs for hours, away from light pollution and below the complexity of spaceflight. Airborne observatories are rarer now, but even temporary campaigns, small telescopes mounted in aircraft windows during a dark stretch, can dodge low-level turbulence and chase clear patches over cloud belts. A dozen such flights over 2 weeks would not produce glossy posters, but they could harvest clean minutes that ground sites lose to weather. Not all opportunism is optical. Radio and microwave receivers can trace large-scale dust and gas in ways that ignore the bright sky. A comet's gas sometimes emits at specific radio frequencies, faint but detectable with dishes that can operate in daylight. Those signals are slow, the way a bass note sustains under a melody. They will not catch a quick jet turning on and off. They will tell you if the overall gas production stepped up or down during the days when sunlight blinded cameras. Sub-millimeter arrays can do a similar job for certain molecules if the geometry is kind and the schedule allows. Then there is a window as old as amateur astronomy, a backyard under a dark American sky. We do not say it often enough. Serious contributions come from porches, pastures, and school parking lots. The power is not in polished mirrors alone. It is in numbers. 100 observers spread across time zones can braid together continuous coverage that a single large telescope cannot afford. If that network follows a simple playbook-accurate timestamps, good focus, notes on seeing conditions, and a clear record of equipment its work can be used to refine brightness curves, to flag outbursts, and to guide where professional instruments spend their narrow night. The phrase citizen science can sound soft. It is not. It is a way to turn a nation's curiosity into data that holds. These windows come with costs that should be named. Spacecraft have pointing rules for a reason. Every off-target look carries risk if it moves the platform near its safety angles or burns precious fuel. Ground facilities keep schedules months in advance to host dozens of projects. An urgent comet request means someone else's night gets slimmed. Even when an observatory can be flexible, the weather may eat the narrow slot. Each time you ask for a side door, you are borrowing from a neighbor. That is why teams write justification memos and contingency plans in plain language. If you are going to ask, you owe a clear argument for why the window is more than a whim. There is also the price of partial information. A solar coronagraph may show a kink in the tail on a Tuesday. Does that kink mark a jet, or is it the solar wind playing with dust? A Mars orbiter may catch a bright core on a Thursday. Is that a real uptick or a processing artifact? Opportunistic data are valuable, but only if they are folded into the larger fabric with care. You do not let a single odd frame steer the week. You ask, what other instrument can confirm the same feature? You ask whether the geometry, the instrument's sensitivity, and the background make that confirmation possible. If not, you file the feature under maybe and hold your fire until another window agrees. Now, a plain language pause on what astronomers mean by target of opportunity and why it matters. In normal operations, a telescope runs on a fixed plan. Targets are set weeks ahead, with exposure times, filters, and backup options laid out. A target of opportunity is a permission slip to interrupt that plan when a short-lived event appears. The interruption is controlled. A panel weighs the request against safety, schedule, and scientific return. If approved, the telescope pivots, takes the data, and then returns to its calendar. This process exists because the sky does not keep our hours. A comet outburst, a supernova, or a near-Earth asteroid flyby will not wait for next month's slot. Without a target of opportunity system, you miss the moments that cannot be replayed. With it, you capture them, but only when the value is clear and the risks are contained. There are clever tricks inside these windows that do not need new hardware. Lucky imaging taking, many very short exposures and stacking only the sharpest can freeze. Fine detail in the inner coma during bright twilight that would blur in a single long shot. Differential photometry measuring the comet's brightness relative to nearby stars in the same frame reduces the pain of a rising background and thin haze. Narrow, well-chosen filters isolate lines that stand above the glow. None of this is secret. It is a practical craft. When the main curtain is closed, craft is what keeps the story moving. We can also think about time in finer cuts. Instead of one long night per week, spread shorter visits across many nights. That cadence catches pacing. It tells you if chemistry rose and fell in a day, or if dust structure drifted across the tail with the solar wind. In the squeeze around the sun, pacing sometimes matters more than depth. You can stack images later to dig deeper into faint features. You cannot rebuild a time series that was never taken. My view, stated simply, is that opportunism is strongest when it is humble. Ask for small things that add up. Respect the missions and observatories you borrow from. Be clear about how you will confirm what you think you see. The payoff is not a single stunning frame to post. It is a set of stitches that holds a gap in the quilt. I also believe we should invite the public into these windows, not as cheerleaders only, but as participants. If you run a school astronomy club in Iowa, your twilight images can matter. If you lead a park night in New Mexico, your log of a faint brightening can matter. We will show you how to mark times, how to focus, and how to write notes that scientists can use. That is not charity. It is a collaboration. There is an American virtue in this approach that I love. It is the knack for making do while building better. When a bridge is out, we set up detours and flaggers and keep the town moving until the new span is up. These windows are detours. They are not where we want to drive forever. They are how we keep the story moving while the main road is closed by geometry and glare. They are honest about limits and proud of small wins. Caught together, those small wins might tell us whether a suspected rotation period holds, whether a green shell thickened or thinned during the bright gap, and whether a tail kink was wind or jet. One more side door deserves a spotlight. Education as observation. Teachers across the country can fold a comet lab into class right now. Have students plot brightness against time, using public images and their own measurements. Have them compare the slope of that curve before and after the glare window. A classroom in Georgia will not solve a tail's physics in a week. It will produce careful notes and fresh eyes. Sometimes those eyes spot an oddity the professionals missed, a small surge on a Tuesday morning. And even when they do not, they produce the next cohort of careful listeners to the sky. That is an opportunistic window that pays interest long after Atlas is gone. There are limits we should not cross. We do not ask a mission to violate safe pointing. We do not promise more than a coronagraph can deliver. We do not let a scattered set of marginal detections harden into a headline. Restraint is part of the craft. If an image is ambiguous, we say so and move on. If a window costs too much in time or risk, we let it close and prepare for the next. The hourglass metaphor holds even here. Some sand is not ours to catch. Still, there is a quiet thrill in these side doors. The way a tale brightens in a coronagraph, and you realize an outburst likely happened when Earth's telescopes were turned away. The way a dusty fan seen from Mars aligns with a twilight streak caught from Colorado. The way a backyard in Maine and a small dome in Arizona record the same pulse an hour apart. You feel the country breathing together, not in panic, but in attention. That is what opportunistic windows give a nation, the chance to take part in careful noticing. Educational pause, brief and practical, on parallax and why a second vantage helps. Hold a finger at arm's length. Close your left eye and line the finger up with a distant lamp. Now close your right eye and open your left. The finger jumps against the background. That shift is parallax. Two separated viewpoints see the same object against slightly different backgrounds. With a comet, a spacecraft at Mars, and a telescope on Earth can measure that tiny shift and use triangles to calculate distance, and in some cases, the three-dimensional shape of the tail or the size of structures near the nucleus. Parallax turns two plane pictures into a depth measurement without touching the object. That is why a modest image from a second place can matter so much. By the end of this bright stretch, the logbook from these windows will not read like a novel. It will read like a field journal, dated entries, short notes, a few sketches, tiny proofs. But when you lay that field journal next to the deep nights before and after, gaps close. The rotation puzzle tightens. The chemistry curve makes sense. We will be able to say not only what Atlas was before the glare, but what it did during and how it looked as it walked back into darkness. And now that we have learned to hunt for side doors and to be content with side views, it is time to step into a different room entirely, the one where imagination is allowed with guardrails on. If geometry and hardware did not bind us, how would we study a visitor like this? What would an ideal mission look like? And what technologies would best earn their cost for the next century of interstellar guests? In the next part, we will sketch that dream with care, not as fantasy, but as a roadmap for what to build, so that one day the side doors are not our only way in. Imagine a soundstage where you control the sun with a dimmer and the wind with a dial. You can bring the light close without glare, slow a dust plume to a hush, then speed it up again to watch the grains dance. If time bent in our favor, that is how we would study 3i Atlas, not as hurried spectators on a sidewalk, but as directors on a set, able to position cameras, send runners, and call for a second take without breaking the scene. This is the chapter where we let design outrun constraint, then tether imagination to what engineering could plausibly deliver in the coming decades. Start with posture, not payloads. In the dream plan, we do not launch in a scramble after discovery. We pre-position a small fleet in a quiet gravitational neighborhood, where spacecraft can loiter for years with low fuel burn and high readiness. From that parking spot, they can pivot to meet a visitor early, approach on a safe lane, and arrive with time to work. One craft is the mothership, a bus with long-range communications, robust power, and a suite of remote sensors. 2 or 3 outriders ride along, each specialized, a gas skimmer for in situ chemistry, a dust mapper for particle physics, and a microprobe designed to pass through the inner coma at high speed and sample the breath of the nucleus. The timeline begins years before the close approach. Survey telescopes flag a faint mover on the edge of the map. The fleet runs a quick triage. Orbit fit looks unbound. Brightness change suggests activity. Angles will be safe to observe. A go decision triggers a transfer. The mothership slews and fires a modest burn. The outriders reshuffle into a trailing formation, and the convoy sets out. The aim is not to match the comet's full speed. No engine in our toolbox makes that cheap, but to steer onto a crossing that keeps relative speed manageable for hours, not seconds. If we can carve a corridor where the same features on the comet rotate into view again and again, remote sensing gains teeth, and in situ passes gain context. On approach, the mothership behaves like a flying observatory. High-resolution cameras pin the nucleus against the star field to refine the rotation state. Thermal imagers sketch hot and cold patches through the coma, revealing where fresh vents lift. A compact radar sounds the shallow subsurface when geometry allows, reading layers like pages of a well-worn atlas. The spectrometers do the long, patient work, one tuned to the warmth of common ices, one to the fingerprints of organics closer to room temperature, one to rare isotopes whose lines are faint and fussy, but decisive if captured cleanly. Together, they write a layered inventory: what is present, in what balance, and how the balance shifts as the sun climbs and falls on that small world. Meanwhile, the outriders fan out like reporters assigned to corners of a stadium. The gas skimmer carries a mass spectrometer that inhales and weighs molecules in real time. It is a careful flyer, tracing arcs that cross density gradients and skirting dust sheets that would sandblast exposed surfaces. Each pass returns a profile: water rising here, carbon dioxide there, a pulse of carbon monoxide when a shadow lifts. The dust mapper trails a few hundred miles downwind. It deploys a small lattice of detectors that record impacts, sizes, speeds, and charges, turning a shred of the tail into a particle-by-particle census. The microprobe is the bravest. It angles through the inner coma once, twice if the first pass proves tolerable, to taste the jets where they cut the crust. It carries armor and a shield that blooms like a flower just before the crossing and folds back afterward, saving the instruments from the worst of the grit. Formation flying near a roaring snowball is choreography, not charge. Our fleet keeps a strict buffer around the nucleus, never loitering in the zone where a sudden outburst could turn a plume into a sandstorm thicker than design. Autonomy is the key. Onboard vision locks onto the faint glow of the near-nucleus coma and steers away from dense strands. Predictive models run in a loop, combining recent images with plume physics to forecast where a fan will be 5 minutes from now. If the model sees a risk, the craft sidesteps, then resumes. We use geometry as a tool rather than endure it as a foe. From one vantage, the mothership hugs a sunward angle where thermal mapping is richest. From another, an outrider sees the tail in profile, ideal for measuring how fast small grains accelerate under sunlight. A third slips behind the comet at a safe remove to read the ultraviolet glow of freshly freed atoms silhouetted against the dark. With 3 eyes, we can tomograph the coma, slicing it into volumes and mapping flows like a weather service charts wind within a storm. Add the occasional parallax with Earth and Mars, and what was a flat smear becomes a living 3D scene. There is room in the plan for careful experiments, gentle, reversible, and honest about risk. A small lamp on an outrider can warm a 10-yard patch of coma for minutes to watch how specific lines respond when heat nudges chemistry without touching the nucleus. A puff of inert gas from the skimmer's nozzle can introduce a known tracer into a jet, allowing us to track mixing and flow. A low-power laser can desorb molecules from drifting grains, offering a surface sample without impact. Done in the right place and time, those nudges reveal cause and effect rather than correlation. Done carelessly, they confuse the scene. The line between learning and meddling is thin. We stay on the respectful side. The mission's crown is a sample, if we dare, not a harpoon or a drill. Those require a rendezvous we have not earned, but a gentle catch of dust and ice grains at relative speeds that a designed collector can handle. Imagine a framed aerogel panel that slides out on a boom when the dust density is modest and reels back in before the risk piles up. Grains bury themselves in the gel like meteors frozen mid-dive. The frame seals, nests in a vault, and chills as if it were a lunchbox packed in dry ice. Done right, the vault holds a vacuum and cold from capture to curation on Earth. Inside, unspoiled particles from another star's nursery wait for needles, beams, and scales our laboratories wield better than any robot. If we bring samples home, we build the chain of custody into the mission from the first drawing. Sterile surfaces, clean assembly, blank controls that fly alongside the collector and never open, so we can prove what the spacecraft brought and what the Earth added. The return capsule lands in a recovery net, goes straight into a mobile cleanroom, then into a permanent one where classes of material are partitioned by how sensitive they are to air, humidity, and warmth. The work is slow, not from ceremony, but from care. We measure the lightest isotopes first before they leak. We image fragile organics before they rearrange. We share the catalogue in stages so that teams across the country can request grains suited to their tools and questions. Data would flow the way the coma flows, steady, organized, tagged by time and position. Onboard compression keeps bandwidth sane without discarding surprises. A save button exists for anomalies, preserving raw frames and spectra in their original form to prevent the odd from being averaged away. Quick look products are published within hours to a public dashboard, with the deeper calibrations following in days and the full pipeline in weeks. The country can watch without needing a degree. A chart of water up, then down. A map of a fan that flickered, a timeline of a green shell thickening and thinning. The work of interpretation stays careful, with caveats, but the view is shared. A short educational pause on what makes those quiet, gravitational neighborhoods so useful. Space has a few points where the tug of two big bodies, like the Sun and Earth, balance out in a moving frame. One of them sits a little beyond Earth on the night side. Spacecraft parked there orbit the point as the point orbits the Sun, drifting only slowly and needing little fuel to hold station. That perch has two gifts: a stable thermal environment for sensitive instruments and a clean line of sight back to Earth for communications. Because fuel use is low, a craft can wait there a long time, then tip out on short notice when a target appears. Think of it as a calm eddy just off a swift river, where you can idle a boat and still be close to the main current when it is time to paddle hard. Back in the lab, the instruments we would want to fund next are not only bigger, they are smarter and steadier. For remote sensing, we invest in rugged spectrometers that hold calibration through thermal swings and radiation hits. For in situ work, we refine mass spectrometers that can separate neighbors in the periodic table cleanly enough to read isotopes without confusion. Dust analyzers that taste a grain and spit back its size, density, and mineral hints in milliseconds keep up with fast flows. Shields and windows that can shrug off micrometeoroid hits without clouding let the mission last longer than a single pass. Autonomy that is explainable, not a black box, lets ground teams trust the decisions made when light time delays are long and seconds count. Navigation deserves special tools. We would field a narrow beam LiDAR to range to the inner coma safely when optical images blur. We would test radar modes that can see through the dust to the nuclear silhouette without saturating. We would equip the outriders with star trackers that do not drop out when the field is full of moving snow, and we would write guidance that respects uncertainty, widening keep-out zones automatically if a plume model diverges from reality. On top of that, we would bake in a culture of drills, loss of signal in the core, safe mode in a plume, a detector that warms unexpectedly. The fleet learns those dances before it meets a real storm. I will say plainly what this design asks from a nation: patience in the build, urgency at the right hour, and openness all the way through. My view is that we should spend our next big dollars on readiness rather than one-shot stunts. A fleet that can idle and sprint, a curation facility that treats alien snow like a priceless letter, and a data system that invites teachers and students into the story are not just comet tools. They are national assets. I also think we should keep our public promises modest and our internal standards unforgiving. When a hint looks good, we check it 3 ways. When a claim will travel far beyond science, we speak with care. Ethics travel with us. We do not carve a comet to suit a measurement we want. We do not leave a cloud of earthly materials in our wake to confuse those who come after. If samples come home, we protect our biosphere with the same care we protect the samples from our biosphere. The odds that an interstellar dust grain holds something dangerous are vanishingly small. The value of proving our chain of custody is large. Trust is a reservoir you fill drop by drop and dump in a minute if you are sloppy. We do not spill. Budget realists will ask for an incremental path, and they are right. We can flight test pieces soon. A single prepositioned observer with powerful remote sensors proves the parking and pivot concept. A pair of small scouts launched together can practice formation flight and dust avoidance near a friendly comet bound to the sun. A free flyer can catch and return dust shed by a comet on a quiet arc, rehearsing capture and curation without the rush of a fast hyperbola. Each step yields science now and de-risks the next. Education is a subsystem, not an afterthought. From day one, we plan classrooms into the data stream, middle school labs built around brightness curves, high school projects that reconstruct a coma in 3D from multiple vantage points, community college internships in the curation lab, shadowing technicians as they handle a grain from between the stars. When a country's students can see their hands on the same chain that holds a priceless sample, science stops being a show and starts being a room they may one day work in. There is also a place for the public sky. The best fleet will still need Earth. When the craft is in the bright geometry, ground telescopes gather the long time series. When the fleet is past the nucleus and reading cold embers, amateurs can watch for late outbursts or odd turns in the tail. The dream mission does not replace the web of eyes. It pays it forward with coordinates, finder charts, and a feedback loop that shows how a backyard image nudged an outrider to try a second pass. If time really could bend, we would pace the comet through a full season. A quiet approach, a loud midday, a measured retreat. We would learn which ices lead and which follow, how jets pulse and migrate, how dust shapes itself before sunlight shreds it. We would bring home motes that taste of a distant nursery and put them under beams in Houston, Pasadena, and Boulder. We would share the curve and the map in real time and show our work in ways that a 5th grader can trace. All of that is beyond this month's reach. None of it is beyond a decade's work, if we choose. The metaphor of the soundstage matters here. It is not about pretending the universe will obey our cues. It is about building enough control over our own tools that when the universe gifts us a once-only scene, we are ready to light it well, record it cleanly, and leave the stage better than we found it. That is a kind of humility that looks like ambition from the outside. It does not bid against the sky, it bids on ourselves. We are close now to the practical pivot. Dreaming is useful if it tells you where to lay bricks. The next visitor will not bend time for us. It will arrive on a date that seems inconvenient, at an angle that asks for patience, and at a brightness that rewards steady hands. Our final step before the hourglass is to sketch the ecosystem that makes readiness real. Early eyes that spot the faint mover, norms that keep data honest and fast, training that turns citizens into co-observers, and dark skies that protect the work. In the next part, we prepare for the next hello. Picture a relay race on a high school track just before sunset. The first runner crouches in the blocks, the second bounces on their toes, the third watches the curve, and the anchor steadies their breathing at the far straightaway. The baton is the next interstellar visitor. If we want a clean lap, the handoffs must be smooth, the lanes kept clear, and every runner drilled on what to do when the unexpected gust hits the home stretch. Preparing for the next hello is not one hero's sprint. It is a practiced relay where each leg is tuned to its strengths and the baton never touches the ground. The opening leg is early discovery. Wide field surveys will comb the sky night after night, turning faint movers into alerts that reach the community before breakfast. Those first flags should include everything a follow-up team needs without digging: a reliable position, a path forecast, a first guess at brightness change, and a quality score that says how much to trust the numbers. The payoff is not only speed, it is a focus. When a handful of objects stand out clearly, medium telescopes can shift quickly to measure color, motion, and activity instead of wasting nights triaging false alarms. Once a candidate looks unbound and active, the second leg begins. The characterization sprint. This is where a network of ground telescopes across the Americas earns its keep. From modest university domes to national facilities, each site does what it does best. Some gather images with crisp stars that freeze jets and faint tails. Others collect spectra that tease out which ices are doing the talking under the early sun. A few specialize in polarimetry to read dust grain texture. The map that emerges in the first weeks becomes the brief for space assets. It says where to look when the chemistry changes and what features seem to pulse with rotation. Spacecraft form the third leg, a stride that needs calm preparation long before the starter pistol. A prepositioned observer cruising at a stable point in space can tilt to the newcomer without risking its life with unsafe angles. It can watch at wavelengths the atmosphere eats and keep going when twilight swallows ground sights. If a small scout can also pivot, the pair becomes a stereo rig. The view is not just pretty. With 2 vantage points, the comet's flows can be mapped in 3 dimensions, and the tail's twist becomes a measurable response to the wind off the sun. The anchor leg is something we do not talk about enough: curation and communication. Data that arrives fast is only half the win. They must arrive clean, labeled, and ready to be checked by another team without drama. When citizens and classrooms can follow along in plain language, the country builds a habit of scientific attention that outlasts a single visitor. Done right, the relay ends with the baton high and the crowd on its feet, not because we promised fireworks, but because the handoffs were graceful and the story held from gun to tape. My view is simple: we should invest in the boring brilliance of handoff. It is not glamorous to budget time for calibration stars, to maintain shared formats, or to rehearse point-of-contact roles for midnight alerts. Yet that discipline is what turns a rare object into a shared success rather than a scramble. I also believe we should judge ourselves less by single-night triumphs and more by how well we make other teams faster. If our work lets a neighbor's telescope capture the key spectrum the following dawn, that is a quiet win we should value loudly. Early discovery benefits from a principle learned in weather forecasting. Small, early signals carry power if they are placed into good models quickly and revised without pride. Survey teams should post not only what they saw, but also how certain they are and what could fool the algorithm. Bright streaks from satellites, ghost images from reflections, and thin clouds can all fake motion. When flags include a humility score, follow-up teams know whether to commit an hour or a night. That triage protects scarce resources and keeps goodwill flowing between observers who will rely on one another for months. The second leg thrives on standards. Observers across the country can speak the same language. If exposure times, filters, timestamps, and processing steps are reported in the same order with the same vocabulary, that sounds dull on paper. It is dynamite at 3 in the morning when a team in Arizona can merge a stack from Ohio without guessing how the flats and darks were made. It also tightens the loop between amateurs and professionals. If a backyard in Oregon and a small observatory in Florida log brightness the same way, their light curves can join cleanly and reveal a pattern no single site could see alone. Educational moment, short and practical, on uncertainty cones and why early handoffs matter. When a new object is found, its future path is not a thin line, but a widening cone, like a flashlight beam stretching into the distance. Each new measurement narrows that cone, shrinking it from a floodlight to a tight spotlight. If follow-up comes quickly, the spotlight gets narrow within days, and telescopes can point confidently. If follow-up lags, the cone balloons. Observers waste time hunting around the edges and risk missing the target entirely in a small eyepiece or a narrow spectrograph slit. That is why a few well-timed positions from different sites in the first week can be worth more than many measurements taken a month later. The baton moves smoothly when the next runner knows exactly where to put their hand. The third leg is where readiness meets restraint. A space observer designed for rapid response should be nimble, but it should also be conservative, near the sun. Safe pointing rules exist to protect instruments and the mission's life. The team can still be bold in the moments that matter most, but the default posture should be steady. A daily cadence of images and spectra, even when the geometry is poor, beats a risky tilt for a single heroic frame. The country does not need a streak of lucky photos. It needs a mission that can watch through an entire passage, knowing exactly when to say no, we will hold the line, and live to see tomorrow's data. Communication closes the loop. A public dashboard where every leg of the relay posts simple summaries can create a rhythm that audiences understand. Short videos that show how last night's spectra confirmed an earlier hint. A clean chart that connects a backyard, brightening to a space image of a growing fan. A daily cadence that feels more like a weather report than a headline chase. When the tone stays measured and the updates are honest about uncertainty, trust grows. The next time the alert sounds, more eyes turn toward the sky and more hands are ready on the baton. We should also think about the physical lanes we run in. Dark skies are not a luxury. They are the track's surface. Shielded fixtures, thoughtful ordnances, and community pride in a Milky Way you can see from town make all the difference when a comet sits low in twilight. Parks, schools, and small towns can lead. A single county that dims glary lights after midnight buys observers an extra half magnitude and lets students see their first faint tail. That choice is as much about civic identity as it is about science. A place that protects its night sees more clearly in every sense. Citizen science can be upgraded from kindness to craft. Clubs and classrooms can adopt small pieces of the relay with specific training. One group excels at timing star dips during occultations. Another log of polarization snapshots during twilight. A third specializes in narrowband imaging that isolates the green sheen near the core. None of these requires elite gear. They require repetition, mentorship, and feedback. When a student in North Carolina sees their number appear in the nightly summary with a note that it helped confirm a pulse in the coma, a habit is born that could shape a career. The data backbone deserves national care. A modern pipeline should accept uploads from many sources, check them for basic quality automatically, and tag them with rich context. Weather conditions, seeing estimates, instrument settings, and processing notes become part of the package by default. That way, a researcher 6 months from now can rerun a result and understand exactly how the sausage was made. Reproducibility stops being a slogan and becomes a button you can click. The baton then carries not only a number, but a full memory of how that number came to be. There is a role for industry that fits this relay mindset. Satellite operators can adjust schedules to keep bright trails away from key fields during narrow windows, a move that costs little and earns trust. Camera makers can publish performance curves that help amateurs pick filters that work under suburban skies. Cloud providers can sponsor storage for public data streams and commit to keeping them accessible at school-friendly speeds. Small moves, executed on time, turn goodwill into capability. My personal conviction is that the United States is especially good at building ecosystems when a challenge is clear and shared. We have done it for weather, for logistics, for emergency response. An interstellar visitor is a gentler challenge, but it asks for the same habits. We should resist the pose of lone genius and lean into the craft of many hands. And we should measure success not by who gets their name in lights, but by how quickly the baton moves. and how cleanly the story is told from first alert to last frame. Training is the quiet fuel. Workshops that pair graduate students with club observers on the same telescope teach both sides how to talk. Summer programs that place high schoolers into data teams let them feel the rhythm of nightly operations. Short online modules that show exactly how to timestamp, focus, and record conditions raise the floor for thousands of contributors at once. The goal is not to build an army. It is to build a chorus that can hold a note through the bright stretch when patience and consistency beat flash. Policy can help without smothering. Agencies that fund astronomy can set gentle rules that reward teams who share quickly in standard formats and who design their projects to involve the public in real ways. Universities can value reproducible pipelines as much as flashy figures when they weigh promotion. Town councils can adopt lighting codes that honor safety and the sky together. None of this requires grand laws. It asks for local choices aligned with a larger picture, where a nation decides to become a better listener to the night. When the next hello comes, the baton will move faster if we rehearse the handoffs now. Survey teams can test alert formats on ordinary comets to polish the flow. Ground networks can practice twilight sprints and midday reductions, so the first days feel familiar. Space missions can run tabletop drills that simulate bright geometry weeks and decide in advance where the line between brave and reckless sits. These rehearsals cost a modest time and save precious nights when it counts. There will be surprises. A visitor may arrive dimmer than expected or brighter. It may turn green late and then fade. It may carry a dust mix that scatters sunlight in odd ways. Surprises are not a problem when the relay is strong. They become the best pages in the notebook. If the baton is steady, each oddity is measured, shared, and questioned by many eyes before it makes the leap from hint to headline. That rhythm is how you keep faith with the public and with the sky. In the end, preparing for the next hello is about choosing what we want to be good at. We can try to be fast alone, or we can become fast together. We can celebrate stunts, or we can build systems that make stunts unnecessary. We can chase moments, or we can practice a careful attention that carries across seasons. The relay metaphor is not just a sports image. It is a civic choice to move knowledge in clean handoffs rather than drops and scrambles. We have one part left, and the image that closes our circle waits there. The hourglass has been with us since the hook, a reminder that urgency can be about learning rather than fear. In the final chapter, we will set that hourglass down on a quiet table, watch the last grains fall for 3i Atlas, and talk about what remains in our hands when the sand has passed and the night is dark again. Set the hourglass on the table and listen. The room is quiet, but you can hear the soft hiss of sand. Each grain is a minute we spent watching 3i Atlas wake, brighten, and slip toward glare. We did not chase it on impulse. We learned to time our looks, to share the view, to hold our claims until the light grew kind again. The last grains will fall soon. That is not a failure. It is the shape of the sky that teaches us how to pay attention. Urgency was never about fear. It was about respect for a visitor who would not loop back. We captured lines that whisper of carbon and water. We mapped dust that rides the sun's breath. We argued in good faith when hints outpaced proof, then tightened the story with cleaner nights. What remains is not only data, it is a habit. Teams that move in step, classrooms that plot their first light curve, communities that dim a parking lot so a faint tail can be seen after dinner. When the glass empties, we flip it. The next hello is already possible because we built handoffs, not heroics. We will be ready sooner. We will talk straight. We will invite more eyes into the dark. That is how a country grows its science, one careful minute at a time. If this companion through the night meant something to you, support the work that keeps it going. Subscribe for the next chapter, turn on notifications so you catch each update, and leave your questions and ideas. Your curiosity is part of the hourglass too, and the sky always rewards those who keep watching.